start?
Yes.
Yeah.
Sorry for the delay.
No delay. It's exactly at 10.
All right.
And of course, this 1 minute delay is not because of me. We met somebody on the way, so we were discussing that. Yeah, good morning everybody, and welcome to the second day of this GIAN program. And today morning we have 2 lectures, and afternoon we have the practical session. Dr. Roy will be presenting the talk on alpha and gamma ray interactions with the matter. He thought there are some participants who are from other areas. So for them some basic information is necessary. So he will be talking about alpha and gamma interactions with the matter in the first lecture, and in the second lecture it's gamma ray spectrometry in laboratory, introduction to the measurements and spectrum analysis.
Thank you, Karannakara. As he told you, this is like an introduction to the laboratory session. I know that you already know most of these things, but I think it's quite good to review once again these things. In this case, how alpha and gamma rays interact with medium. All right. So,
yeah,
perhaps I put this one here. So, all right. So, this is the basis how we detect radiation. So, it is based on interaction between the radiation and the medium. In essence, the detector material. And once more, radiation produces a signal in the detector material. This could be the detector material here. And the data processing system changes, or signal processing system changes the signal into a form that can be calculated, collected, or sorted according to the type of information we want to have. And usually what we want to have is a spectrum. So charged particles ionize medium and interact strongly. Particles like these, neutral particles, gammas, neutrons, they interact less and penetrates farther. So there are a lot of charged particles, of course, electrons, positrons, alphas, muons, protons, heavy nuclei, etc., etc. So they have different interactions, inelastic interactions with electrons. This is very vital to understand. It's an interaction with electrons of the medium material. So there is ionization process and excitation process. Of course, elastic scattering from the nuclei of the medium can happen. And then there are some other phenomena like Bremsstrahlung, Cherenkov radiation, annihilation radiation, these kind of things. And these are the main interactions for uncharged particles. I mean, in this case, photons. Photoelectric phenomenon, Compton scattering, and pair production. In case of neutrons, elastic or inelastic interactions are very important. All right. So, you have to understand that especially environmental samples often contain beta-emitting radionuclides, which means that these betas may cause signals to gamma spectrum and also to alpha spectrum. We have to understand that too. In this case, Bremsstrahlung is happened and the electron loses a little bit energy. Interactions, I mean ionization mainly, between alphas and electrons of the material are the main energy loss mechanisms. So it's alpha and electrons. Sometimes interactions happen with the nuclide, but not very often. So, as you know this, perhaps I can see easily if I am here. But the letters are so small, I have to go back, sorry.
Yeah.
But you can perhaps sit there if you like, so that you can see. Please sit there. So these are the examples of Compton scattering that I will consider in the next slides. Pair production and subsequent annihilation, which happens here, and photoelectric phenomenon. I know that you all know these things, but it's good to review these. All right. Here you can see photon attenuation in terms of square centimeters per gram in the vertical axis, and here is the energy of photons. So, as you can see here, in the low energies, less than 100 kilo electron volts or so. I guess this material is from lead. I forgot to put it in here. Main area in terms of energy is between around 1 MeV down to 0.1 MeV. Then pair production rises. So, do you have any idea what's this phenomenon? Yeah. Yeah. All right. So, interaction probability depends strongly on the atomic number and, of course, the photon energy. And as I explained in the previous slide, photoelectric effect is dominant in this area. Pair production here, this area, and Compton effect this area. In case of germanium, which is the material for gamma ray detectors, mainly high resolution gamma ray spectrometers. So the limits are here, okay, 100 kilo electron volts, 2, 3, 4, 5. After 5 MeV, pair production is dominant. So since we are in the present course, we are dealing with alpha and gamma ray spectrometry. The medium materials in the following slides are considered only germanium and silicon, which are the most relevant detector materials in high resolution. Of course, I will later talk about scintillation material things. And as you've noticed in yesterday's lab session, alpha particle energy loss in air is relevant, and that's why alphas are measured, alpha spectra are measured usually in vacuum chambers. But as I mentioned, electrons and beta rays has also a role. Okay, let's look at the interactions between alphas and medium matter. Ionization and excitations, they are the primary mechanisms. For alphas, the energy loss per ion per formed is on the average 35 electron volts. And for example, if we have a 5 MeV alpha particle, it means that 100,000 around 100,000 ion pairs is produced. And I'm sure that you know that the range of alpha particles is very short in air, around this size, some centimeters in air. So, and if you want to calculate alpha particle range in the air as a function of energy, you can use, for example, this empirical relation. Now you have to understand also that interaction with nuclei, not only interactions with electrons, may happen. I will show it soon. Okay, these are ranges of alpha particles. In this case for silicon, this case for air. This is the range. This is the original alpha energy in MeV. So there is a difference around 1000 between these two. So for example, in silicon, the range is 20, 30 micrometers for 5 MeV alpha. So, what is stopping power? It is the energy loss per unit path length. And in this case, it is expressed as units of megaelectron volts per meter. It can be calculated by using this equation. I will not go through these details. You can later check them. But the calculation is basically not very complicated. And this is so-called Bragg curve. So this is the path length, and this is the stopping power here. And at the very end of the path length, in this case, the original energy of alphas is 5.5 MeV, which is close to the americium 241 alphas. So at the end of the path, the ionization is emphasized. But alpha particles straggling, in essence, statistical fluctuations. It is the number of collisions between the alphas and the medium material, and this may vary the range a little bit, not very much, but a little bit. Okay, you can see here is a alpha source, very thin source, alphas going this way to the material. And for example, this is a typical alpha particle track. It's a more or less straight line. And at the very end of the track, the ionization is very strong. These spots refer to the ionization. Ionization, so alpha kicks out the electrons of the medium material. But for example, in this case, the interaction or here may happen between alphas and the nucleus itself. So the ionization is very sparse in the beginning of the path, but very dense at the end of the path. So this is totally different compared to the path of electrons. So this is alphas, very straight line, but electrons go like this. But in this course we are not dealing very much with electrons. We concentrate on photons and alphas. All right. How the detector properties and the material between the detector and the source influence the alpha peak shape. So in principle, the emission of for example, polonium-210, it emits only one alpha particle and the peak should be very, very narrow. However, our detectors are not perfect. What we are seeing is like that. So there is a Gaussian part of this peak and some low energy tailing. In this case, neptunium, it's a little more difficult to analyze because of several peaks. Some transuranium elements has only two main alpha emissions. All right, we discussed very shortly yesterday these things, but so what could be the thickness of a high-resolution alpha detector composed of silicon? So it is around 100 or 200 micrometers. And it should be not too thick because it's from the perspective of alphas, it's no use to have a thicker detector. And in addition, other interactions, I mean photon interaction in silicon detector may only happen, and it disturbs the alpha spectrum. So, because the range of alphas is very short in samples, so what about this question? Let's suppose that you will obtain an environmental sample, such as soil sample, with mass of 100 grams or so. So you have to analyze polonium-210 from the sample. How to proceed then? I'm sure you can explain this. So what you have to do is you have to do probably radio element separation, and you must process the sample as a very, very thin layer so that you can have a good alpha spectrum. If the thickness is big, then there is a mess in the spectrum. However, you can analyze also those kind of spectra. I will show that later. All right, let's go through gamma ray interactions. Okay, these are the main mechanisms: photoelectric absorption, Compton scattering and pair production. There is also Rayleigh scattering, but it's not very significant. So how these are visible in the gamma spectra? Let's see. So this happens in very low gamma energies, less than 100 kilo electron volts. So incoming low energy gamma ray is absorbed and an electron is ejected. However, what happens here is that electron shells, they are rearranged. For example, this photon kicks out this electron here, which means that there is an empty hole in the electron shell, and electrons coming from the outer shell may drop down, and that means there is an emission of X-rays. But if you want to calculate the kinetic energy of this electron, you have to take into account the binding energy. And as shown in one of the previous slides, you can see here the binding energy edges from different cells, M shell, L shell, and K shell. K shell is the innermost. This is L shell, etc., etc. So interaction probability depends very strongly on the atomic number, very strongly, and also inversely proportional to the energy of gammas. So this means that it is important only for low energy. And this means that this Z5, it means that lead absorbs more than, for example, carbon. Let's look at Compton scattering. I'm so sure that you have looked through all these equations in your studies. Professor Compton investigated these things 100 years ago or something like that. If I remember it correctly, he got Nobel Prize for these equations. I'm not sure about that. So what happens here? So there's an interaction between the gamma ray and almost free orbital electron of the medium atom. So part of the gamma ray energy is transferred to the recoil electron. This is the recoil electron, this one. So this is in gamma ray spectrometry for environmental samples. I think this is one of the most important mechanisms. But also pair production may happen in case of high energy gammas. But the energy must be 2 times the rest energy of electron. So it's in fact, it's a materialization of an electron and positron pair here, close to the atomic nucleus. And the photon disappears. And the emission or the photon energy is divided between these two particles. And what may happen is annihilation of positron when it hits to normal material. So this is antimatter, this one. It may cause single or double so-called escape peaks and an annihilation peak, which is 511 kiloelectron volts. All right, let's go on. So, if you take into account previous slides, it is so that size of the detector and also other things too determines how above mentioned interactions processes are visible in the gamma ray spectrum. So interactions may happen close to the surface of the detector or deep, or perhaps no interaction at all. It might happen. So let's assume that we have a very big detector, like this one. And let's assume that now in this picture I'm not considering the surface effects. That's why there is this hole. And photons are coming here this way. So detector is very big. What happens? So no particles are coming out of this detector because the detector is very big. What happens? What we detect is we detect a full energy peak, nothing else. And this is a good thing, very good thing. However, if the detector is small, what happens? There are gamma ray interactions close to the surface of the detector. Okay? In the case of photoelectric absorption, photon disappears, and the energies of the electrons are quite small, so that quite often it happens that all the energy stays in the detector, but not always. In case of Compton scattering, it may happen that photons escape the detector, and what we are seeing is the Compton background. And same thing holds for pair production. It may happen that the high energy electron, quite high energy, and positron, they may go out. So what we see here is, okay, we see of course full energy peak, which is our primary interest. We are interested mainly on these so-called photo peaks. We are not very much interested on these Compton areas. They are disturbing our spectrum analysis. As you will see perhaps today or tomorrow or Thursday. Let's look at the realistic detector. So it's size is like your detectors here in your lab. So what does this intermediate mean? It's detector dimensions are comparable to the mean free path of secondary gammas. So it means that in several cases, all interactions or all electrons or photons, they stay inside the detector, but some may escape from the detector. This is the interior part of one of our decommissioned gamma detectors. So you can see here, this is the active part of the detector. So it's in fact, it's not very big. It's quite small, in fact. So this is the most important part of the detector. Of course, other parts are too. Important, but the detectors are not necessarily very big. So we can see here in the spectrum, we can see full energy peaks, but also so-called single escape peaks and double escape peaks. So do you have any questions in this phase? Is it too simple or too complex things? All right, let's continue. Please ask me if you have any uncertainties about these things I'm explaining. So, this is the simplified scheme of the detector response function. And what we are interested here is this full energy peak. We are not very much interested on these peaks or this background here. They are disturbing our gamma ray analysis. There are single escape peaks, double escape peaks. There may be annihilation peak, backscattering peak, X-ray peaks, etc. All right, let's explain some of these phenomena. Okay, let's assume that this is the detector and this is the lead shield here. So why we are using lead shield? To prevent photons coming from the walls or from your body to the detector. That disturbs the detection of photons coming from the sample itself. However, it's not necessarily a good thing that we have lead shield here, because there might happen secondary reactions. For example, in this case, let's assume that the source is here. Because of the Compton scattering, the photon may go through the detector and scatters here, so-called backscattering. So it would be better to measure photons without any lead shielding. But there is radiation all over in the university, so we have to use shielding. And in this case, it may happen that the photon goes this way to the lead shield, then characteristic X-rays may come out there, and they are typically lead X-rays, energy of 80 kilo electron volts or so, 70. And also annihilation may happen, which means that this 511 peak may be detected, as shown here. So this is backscatter peak, this is X-ray peak, this is annihilation peak. You have to remember that these X-ray peaks can come also from the sample itself. You can please look at the LARA application that I showed you yesterday. In each emission, or practically in each emission or decay process, the nuclide emits also X-rays. However, their energies are much lower than typical gamma, so they are located also in this energy area here. All right. Okay, these are, I will show you some, let's see, all right. I will show you some examples. These examples, example spectra I obtained some years ago when I made efficiency calibration of our detectors. I used in the efficiency calibration, I used two kind of sources. One source contained only lead 210. Another source contained a mixture of different nuclides. I will explain this later, but this is spectrum is from a americium-241 source. This is the main peak of americium. Let's zoom this spectrum. It's this one, so 59 kilo electron volts. There are other small peaks here. So what are these peaks? X-rays from americium, indeed. From what shell? They are in fact L X-rays, because K X-rays would be somewhere much higher. But americium do not emit very much K shell X-rays. All right. So, what's this, for example? Please, Avanis, you can explain. In fact, what happens in the detector when a photon goes there? It may happen so that K electron K electron emission energy is around 10 kilo electron volts. What may happen? Let's go back a little bit. Okay, let it be this one. If this interaction happens very close to the surface of the detector, what might happen? It might happen so that this K electron goes out of the detector. So there is an energy loss, and in fact, because the americium energy is so low, interactions mainly happen close to the detector surface. So it's a germanium escape peak. This one. So not all the energy is detected. And same thing also happens here in this area. Part of the electron energy stays in the detector, and other part of the energy is lost. So this is typical phenomenon in low energy gammas. All right. Let's look at cesium. As you know, the emission energy is 260. So what you can see here is a Compton edge, this one. There is a backscatter peak coming from the lead shield. Backscattering from there. And these are barium X-rays. And these are generated by the decay of cesium. The energies here, they are 32 and 37 kilo electron volts, if I remember this correctly. But you have to understand that cesium is a beta emission nuclide, so betas may also go to the detector. But we cannot see those. The beta energies are quite low in this nuclide. So the gamma detectors detect also betas. For example, I have done some measurements from strontium-90, by using gamma, our gamma ray spectrometer. So there are no peaks in that case. Okay, this is cobalt-60, very typical radionuclide in gamma ray laboratories. It mainly emits these two gammas here. Energies are shown here. Compton edge of this peak is located here, and from this peak it's located here. There is backscatter peak here. Annihilation peak is very small in this case, because the energies here, they are not very big. Annihilation peak would be quite big if the energies are higher. What is this peak? So you can see that there are some, in this case, if this level 3 goes directly to the base level, but the emission yield is very, very small. However, this is not very big, but anyway, it's quite big. Why? You have to understand that the energy resolution of typical multi-channel analysis, it's an order of microseconds. But this happens within nanoseconds or picoseconds or something like that. So it may happen that both of these photons goes to the detector basically at the same time from the point of view of the multi-channel analyzer. So it's a coincidence effect. And this coincidence effect is a very nasty effect, in fact. So in some nuclides have strong coincidences, and in the spectrum analysis phase, it may cause a lot of troubles. All right. Okay, this was it. Do you have any questions, comments? Is it too simple, this one?
Sir, from the forward step draft, I've seen the baseline is downward drafting. Why this happening?
Sorry?
The baseline is not in a straight line, it is downward drafting. Why that is happening in that spectrum?
You mean this?
That part is okay, but after the 1173 keV, the baseline is coming downwards.
You mean that?
After that, the baseline is coming downward.
Yes, it goes down.
Why it is happening?
Yeah.
Why it is not straight?
Multiple quantum scattering is possible. If you mean these counts here, yeah. And these counts here, they may be those cases when, for example, this photon stays, or the energy of this photon stays in the detector, but this photon coming at the same time, practically, the detector detects only part of this photon energy. So these are also coincidence, how to say this? These are because of the coincidences, but there is no peak in this case, because some of the peaks some of the photon energy came out of the detector. So coincidence effect means also that these peaks go lower. They are not anymore as high as normal. Any other comments, questions? All right, I hope that this presentation was not too simple for you, but I have to explain this. All right, but Could we have a short break? What's the time now? Shall I have 13 minutes? So should we come back here 11 o'clock? No? Okay, thanks very much. Sorry, because of this noise, I can't hear. Can you?
Be louder.
Sir, can you explain coincidence effects?
Coincidence effect. Okay, once more. This is a detector, this one. This is a sample. Sample is usually put in this way, above the detector. What happens when there is radioactive material there? It might happen so that let's put it this way. So this is the detector. Let's assume that this is the sample. And a decay process happens, for example, here. So most of the photons go this way, this way, this way, but some of them goes here. And interactions happens here. But what's the coincidence effect? It's this one, because this cobalt-60, it emitted 2 photons at the same, more or less at the same time. It may happen that both photons are coming here. So what happens in the MCA, in the multi-channel analyzer? It doesn't detect energy of this photon only or this photon only. It detects some of these energies. So this is called as true coincidence. There is so-called random coincidences too, which is the fact that if this source is very active, several kilobecquerels or even megabecquerels, it may happen that let's assume that there is another nuclide here, which also decays. Photons can go that way or this way. However, because the time resolution is only 1 microsecond order of magnitude in the MCA, it may happen that this photon is detected at the same time as this photon. So this is so-called random coincidence. It's a very nasty phenomenon, and it causes sometimes very big problems in the spectrum analysis, especially if there are several peaks in the spectrum. Did you understand this? Is it okay? No? Okay.
Some more questions?
Okay, you can ask me later. It's not a problem.
Yeah.
I answer.
But you ask questions. Any doubt, you ask questions.
Yeah,
So she asked, he nicely explained it.
it's a good question.
Yeah.
Really, because this is very important effect in gamma ray spectrometry, and as I told you, it disturbs quite often the analysis. All right, thank you very much.
Yeah. So we break for 5 minutes when we accept.
Is he coming? Ah. All right. Fine. All right. Let's start. You already saw gamma ray spectrometers in the lab. Let's go through in this presentation all those things once more so that you can have a good impression what happens when we do measurements and spectrum analysis. So these are the contents. What is a gamma ray spectrometer? How the spectrum is generated? How activity or activity concentration is calculated? I have a short, some slides only for the peak efficiency. I will talk these things later. What are the requirements for the sample? What does the spectrum analyzer do? And a short summary. All right. So this is a gamma ray spectrometer. The detector itself is located in this part of the detector. This is lead shield. This is the cooler or devar. There is here at least liquid nitrogen, temperature around -200 or something like that. So what happens in the measurement? So the sample is just put on the detector. It's a very simple process, basically. This is a zoom picture. This is the sensitive part of the detector of the radiation. In this case, the diameter might be 7-8 centimeters, thickness around 3-4 centimeters. Not very big. This is so-called planar detector, this one. And this is the detector window. Radiation, gamma radiation goes through that window. If we want to detect very low energy gammas, we should have a very thin window. In older detectors, this window is quite often composed, for example, aluminium, which is also quite good material, but then we cannot see very low energy photons. This window could be also, for example, beryllium material. All right. So, once more, this is so-called active part of the detector, this one. This is an X-ray picture of one of our detectors. So what happens in the detector? This is the detector itself. So gamma goes, for example, this way. Electrons and holes are produced, and signal processing system collects the signal, analyzes it, and put the data into a multi-channel analyzer, from which we get a spectrum. Okay. This is one of our detectors. Lead shield is like this. We have a devar this part of the detector. We don't have here in my organization anymore those analog measurement systems. We have only digital ones. So you cannot see practically here the MCA. Let's look at what happens here. So this is one of our samples. I will explain later. So putting the sample is a very, very simple thing. There is not a complex process. After measurement, 1 day, for example, then sample is taken out. All right. So how the spectrum is generated. I explained the basis in the previous lecture. Let's look at closer the things. So we have peaks in the spectrum. So how we do the radionuclide identification? It is because of the energy. For example, in this case, the energy is 364 kilo electron volts, which means, according to the radionuclide library data, this is iodine. So, how to calculate the activity? It is based on the peak area. How many counts are in this peak? Basically, it's a quite easy process, but not always. This is only part of the spectrum, not the whole one. All right. So, these peaks appear so that, let's assume that this is a detector, and photon comes to the detector. What happens? They may have multiple interactions or only one interaction. The point is that all the energy is detected by the detector, and we found those peaks. However, the problem, if we can call it as a problem, there is a so-called baseline or background. If the photons leave only part of their energy in the detector, like in this case, or in this case, there are no spikes, but a continuum. We call it as a baseline. It's not the same as detector background. It's a little bit different concept. Background means that we can measure gamma spectrum without any sample. So, how the activity is calculated. So, analyzers of the spectra have to take into account several things when they determine activity or activity concentration. These are the things that he or she must take into account. For example, correctness of the source data, sample type and quality. What do you want from what kind of result do you want from the spectrum? I mean, what are the nuclides to be analyzed? We are not usually analyzing all the nuclides, just the important ones. Spectrum quality, I mean that the quality that, okay, some peaks may be quite wide, resolution might be bad or something like that. In that case, the spectrum might be no good and we have to do another measurement. So we also have to take into account activity equilibrium of the radionuclides. I mean this, that in most cases we analyze, for example, if we want to analyze, for example, this iodine here, we detect the peak of iodine. But in some cases, if we want to analyze, for example, radon, which is possible for gamma ray spectrometry, then we do not detect peaks of radon. We detect peaks of its daughter nuclides. Okay? You are analyzing here natural radionuclides, but in some cases, at least in Finland, we might have some additional man-made radionuclides in the sample, and we also have to take into account detector background. I mean, this background is so measurement without any sample in the lead sheet. All right. So how to calculate activities? I will show you an example here, but let's see this. So this is activity, or this case activity concentration C, because of the sample quantity here. Quantity in terms of mass, in terms of volume, for example, per cubic meters or per kilograms or per liters. It depends on the sample. It may be water sample, then we calculate becquerels per liter. If it is air filter sample, then becquerels per cubic meter. All right. So the equation is very simple, basically, very, very simple. So this is the peak area. How many counts are in the peak? Basically very simple. Then we divide it for the measurement time. Very simple. 1 day, 1 weekend. Normally in Stuk, at the weekends we detect, we don't change the samples, so the duration of one measurement could be 3 days or something like that. Okay. This is the library data. So it's a gamma emission yield of nuclide. This is perhaps the most difficult thing. We have to take into account detector efficiency. And I will explain this later, but it means that not all gammas go to the detector. Most of them goes in another direction, and we have to take that into account. And a lot of different effects. And then there are some corrections that must be taken into account. One thing is this coincidence correction that I explained. Also, decay correction must be taken into account. So when we report activity, we have to report also so-called reference time. Because nuclides are decaying, we have to determine the time to which this activity is calculated. So basically, this is very simple equation. Let's have an example. All right. Let's analyze the activity of cesium-137 in this case. It's this peak here, and the equation is here. So let's assume that the number of counts in this peak is 3,000. Please remember that you will get all these notes. Karuna Karavel will send these you later. Okay? Number of counts, 3,000 here. Just an example. Let's assume that the measurement time is 1,000 seconds, almost 20 minutes or something like that. on the basis of the library data. This is the gamma ray yield. How many gammas are emitted by one single decay. Let's assume that the peak efficiency at this energy it is 0.02. So only 2% of gammas are detected. I will explain this later. And the sample quantity, this one Q, let's assume it's 1.1 kilogram, 100 grams. And let's assume that there are no corrections. I hope I understood or calculated this correctly. But the result is this, if you substitute these things to this equation. Not very complex issue, basically. All right, let's look at very shortly about the peak efficiency things. So, this is photon energy here. It's a logarithmic axis. Logarithmic axis is also here. This is the so-called peak efficiency. So, we call our detectors as a short symbols. For example, here V6. It's name of our detector, one of our detector. So I made the calibration so that I have a sample beaker diameter like this, thickness around this, filled by water or almost water. We call this T20 calibration. It's our internal symbol only, nothing else. It is explained here. So what we do when we have a sample with different characteristics, for example, different elemental composition, different size of the beaker, we use so-called efficiency transfer software. I will later explain this part too. But how to interpret this efficiency function? Your function here is almost the same as this one. But you are not detecting very low energy gammas. You are detecting gammas above this point here in this area. This detector can go down to around 10 kilo electron volts. So let's assume that gamma ray energy is 100 kilo electron volts. So what's the efficiency? It is around 0.18 or 16 or something like that. It means that if 100 emissions happen, we detect, in this case, 16 or 18 gammas. So the efficiencies are not very big. All right, do you have any questions on that?
Question? Because this is the efficiency is a very important parameter.
So it is important in the case if we want to have quantitative results, and that is our goal, of course. But we can, of course, sometimes just want to identify the nuclides. Then there is no need to know the efficiencies. All right, let's go further. All right, why the shape is like this? So let's look at first area here. So what happens in your sample? Nuclides decay, most of the gammas go out. Detector is assumed to be located here. So this can be called as a geometric detection efficiency. So most of the gammas doesn't reach the detector. All right, let's look at the gammas that reach the detector. Of course, in this case, it might happen that some photons go through the detector. And that is one of the reasons why this level is not higher. If the detector would be thick, then probably this part of would be much higher. So the maximum efficiency is 1. All right, let's look at closer small energies. So what might happen? It might happen so that all the gamma interactions happens in the sample itself. It is called as self-absorption. So we don't detect not very many photons. That's why the curve is decreasing very rapidly down there. And of course, some of the photons are absorbed in the detector window too, which is very thin, but it may happen. All right, what about this size here? It is because some of the gamma quanta pass through the detector, like this one, without interaction. And this way too. Or do not leave the full energy in the detector, like this one. There is Compton scattering, for example, and the gamma goes out. So this is the reason, these are the reasons why the shape is like that. Please note the logarithmic axis. Okay, there are several types of detectors. Some of them are not so efficient, for example, in low energy gammas. So this is the same curve as I showed you in the previous slide. This is the energy of lead 210. Emission energy is 46. This is the another detector with aluminum window. Window is quite thick, which means that these photons cannot go through the window, or only a small part. We call this detector as G2. It's an internal symbol. So can you explain, okay, you don't know the detector type, but can you explain why efficiency is here higher than for this detector, which is planar detector? Do you have any suggestions?
It will interact with the thickness.
Yeah, the reason is that I don't remember the dimensions of this detector. Probably it's like that. So this B6, it's like this one. B6. I think that G2, it is something like that. So this is longer. I hope I'm correct, because I don't remember the details of all of our detectors, because we have 18 detectors of our lab and I have a bad memory. Any comments?
Question?
All right, if not, let's continue. So I explained to you that very shortly this efficiency transfer method. I will show these things later, but these are the beakers that we are using in our measurements. Do you have these beakers? These are so-called Marinelli beakers. Okay, you don't have these. I will explain soon. But this is an example of one of our detectors, and can you see this one? The source is located here. Why? So I can say you that it was several years ago. I measured 1 gigabecquerel plutonium-238 source using this. So normally you cannot put on the detector megabecquerel sources. The so-called dead time is too large. But gigabecquerel is even 1,000 times more active. So this is plutonium source, but the point is that this plutonium nuclide, you can check this in the LARA application, it doesn't emit many gammas. So we wanted to qualify this source, what kind of source it was. It was used in some studies on biological things, how alpha particles reacts cells of your body. But let's neglect that. Okay. Regarding this beaker type, so it's a so-called Marinelli beaker. Why we are using those kind of beakers? Any ideas? So we want to have as high efficiency as possible, but we also want that number of or the mass of the sample is as much as possible. So we try to put all material as close as possible to the detector. So gammas may go from here to here or here to here. So this distance in those Marinelli beakers we are using is always the same, 3 centimeters. So the volume of this beaker is half a liter. We normally measure water samples using these beakers. Sometimes soil samples or other things. All right. So, what about the samples? What are the requirements? So, one thing is that the sample must be homogeneous if you want to have quantitative result, correct quantitative result. So we have to know the density, height of the sample, and also the elemental composition, so that this our efficiency transfer method works correctly. You have a little bit different approach in your laboratory here. So we have only one efficiency calibration of each detector, except those Marinelli detectors. We have some of these too. But I think you have several calibrations. You mentioned, is it 16 or 18 calibrations?
Yeah, more than 10. We have RGU, RGK, RGTH.
What is asking the type of container?
Container.
Yeah, we have containers in 5 gram of sample, 25 gram,
Yeah.
125 ml,
250.
250 ml like that.
5
Yeah.
And we have sample holder for air filters.
But,
Disk type.
but in those cases you are using, if the sample size varies, you use different calibrations in the background.
We have reference material in the same
Yeah,
geometry.
yeah.
We can show that. In our
But my point is that, I will show it here. So, in the beginning, when I came to Stux Gamma Ray Lab, we had a more or less same kind of system as you have. Okay, we have 18 detectors. Each of the detector, if it would be the same case as you have 16 calibrations. If we want to take into account the coincidence effect, which means that we should also, I will explain this later, we have to also take it into account so-called total efficiency, which means that the number of calibrations is, I don't want to multiply this just now, but the number of calibrations would be too large. My job would be so that I would do nothing else but calibrations. It's a waste of time. Then I decided what to do, and that's why we are using now this efficiency transfer program. I will explain that later. All right. So we also should know the elemental composition too, because it affects the efficiency in case of low energy gammas. I will show that part also later. So this is a homogeneous sample, this one. So the nuclides shown here as red spots are homogeneously distributed. This is not a homogeneous sample, because there are a set of nuclides here, not here. This is either from the point of view of gamma ray spectrometry, it's not a homogeneous sample. Basically it's homogeneous, but surface is a little bit tilted. This is a little bit, how to say, not a normal case, but if we want to determine radium concentration or radon concentration. So what happens in case of radon? It may go to this place, and if we want to analyze radon daughters, so most of the radon goes here, not much here. So this is not very homogeneous from the point of view of gamma ray spectrometry. So the sample must be homogeneous, like this one. So, as explained later, Avanas explained this later, what does a gamma spectrum analyzer do? So, at first, the analyzer checks the validity of the sample data. I mean, beaker type, is it correct? I mean, this refers to the efficiency. Is the reference time, is it okay? We have seen some mistakes happened. Is the so-called quantity, it's not a quantum, but it's a quantity of the sample. Is it okay? Is sample density okay? And some other relevant information. So in this phase, the analyzer do not necessarily check the spectrum itself. He or she checks that the basic data for the sample is okay. In this case, I'm sorry that this is in Finnish, but this is the sample description we are using it for this sample. It's a Marinelli beaker. This is so-called reference day for which we calculate the activity. This is the amount of water, in this case. It's 1.7 liters, yeah. Then there are some other information. Measurement was started at this time. Its duration was almost 1 day. This is detector so-called G4 and using Marinelli beaker. Height of the sample, 3 centimeters. Density, because this is water sample, density is 1. But in this stage, no spectrum analysis, not yet. We have to check the validity of the basic data at first. But then we have to go to the analysis of the spectrum. All right. In my organization, we do the spectrum analysis automatically. So it means that there is a process that identifies each peak and calculates the activities. So it's an automatic process, but we have to check this process or the result of the process manually. For example, like in this case, it might happen that the peak shape is incorrect because of some reason. For example, in this case, the peak area is 3,500. We can do manual analysis, and the correct value is almost 6,000 counts in this peak. All right, some samples may contain very many different radionuclides. This is an example of quite challenging gamma spectrum. In this case, there are almost 200 peaks. I have seen some spectra that contains 400 peaks. So it's a very tedious work if we want to analyze all these. But normally, we analyze only some of these nuclides. But let's look closer at the peak, at the energy of this. All right, you can see the peak here. I think that at least some of you knows what is this peak. So there is uranium-235. Emission energy is shown here, quite close to 186. But there is also radium-226. Emission energy is practically the same, but the yield is very small. In this case, peak fitting, okay, it may look like quite nice, but we do not rely on this because the peaks are overlapping too much. This is typical in sodium iodine detectors. Resolution is quite poor, but these things may happen in high purity germanium detectors too. Not very often. So in this case, if we want to analyze radium, we will analyze radon progeny. Lead 214, bismuth 240. But how to analyze, or what are the requirements of the sample? Because our normal beakers, they are wrapped in this case as a foil because they are not gas tight. And you can see radon disintegrates to radium, disintegrates into radon, which subsequently decays to lead and bismuth. The problem is this radon. It may escape from the beaker. I think that, is it so that your beakers are quite tight?
Seal it with
You seal it? Yeah.
and cap it tight.
Yeah, all right.
Although it is tight, we seal it.
We use vacuum packaging. It's a very simple process. But what we do is that at least the beaker must be full of sample to avoid inhomogeneity and to ensure that there is equilibrium between radium and its daughters. We have to wait 3 weeks. Why 3 weeks? So the reason is this one. Half-life close to 4 days. We want to have equilibrium. This is the reason here. And this is very important. You have to, if you are using this decay chain or mother-daughter analysis, you have to verify that there is equilibrium. Because, for example, for these nuclides, uranium-238, thorium-234, and protactinium-234M, they might be in equilibrium or not. But this is quite difficult thing in some cases because for example, some biological vegetables may absorb, I don't know the correct term, but I call this as absorption. They are absorbing thorium very much, which means that there is excess of thorium in relation of uranium. Well, you can in this stage, if in this phase, if you want to have equilibrium, what could be the waiting time? Any idea? 24 days. How many months?
6 months.
Okay, 6 months. Quite okay. Then there is equilibrium. But in this case, you do not need to wrap the sample because these are not gases, they are metals, they are not escaping from the sample. All right. Oh, so advantage of gamma ray spectrometry is that in principle it can be used to detect almost all radionuclides, but there are some exceptions. The gamma yield must be large enough. For example, in case of plutonium-238, the yields are very small, so it's quite difficult to detect plutonium-238. However, alpha spectrometry is much better. You can see these are the energies of alphas, these are the yields. Total sum is 1 in this case. Total sum here is not 1 in case of gammas. So that's why alpha spectrometry is better than gamma ray spectrometry. But you have to do sample processing, which is very tedious process. All right. So, one slide summary. Why gamma spectrometry? It's a good determination method because with the exception of a few radionuclides like tritium, carbon-14, strontium, almost all radionuclides can be detected by gamma spectrometry and by using just a single measurement. However, the measurement time in some cases must be long enough. All right? The method detects radionuclides with short lives very sensitively. This means that the nuclides sends automatically information from themselves. We don't have to kick them. Please send us information. They send us information by emitting gammas, alphas, etc. However, in case of some nuclides like thorium-232, uranium-238, they send us information too sparse, too slowly. That's why ICP-MS or alpha spectrometry might be better. Advantage is also that sample processing is very simple. Just put the sample in the beaker. Well, this is not exactly the thing. For example, in Stuk we dry all the samples very carefully. Sometimes you have to ash, you have to burn the sample and put the ash into the beaker. But it depends on the case. But basically it's a simple processing compared to the radiochemical processing used in alpha spectrometry. So I already explained this. So it's a so-called passive method, which is not a good definition because we actively do something, but the point is same for alpha spectrometry. All right. This is my last slides. Do you have any comments? Is it too simple? I tried to explain same thing that Avanes told you yesterday. Please note that you will get these presentations later, so maybe you would like to see them again.
Sir, I had a question.
Please.
Okay. So you showed me about the equilibrium between the uranium and the proactinium or something like that. Yeah. This thorium and proactinium. So is that ensured in soil samples?
In soil samples, I have thought this a lot, and it depends on the case. For example, if it rains a lot, and the rain might contain acid, a little bit, not much. So it may happen. I'm not a chemist. I don't understand these things very well, but thorium might. What's the concept in chemistry? Leach, yeah. So leaching may be different in those cases. But in case of rock samples, then I think it's leaching is not. But you have to have every time this think about this equilibrium. Leaching is a very relevant thing.
Now, if those are if I assume that is in equilibrium, then I can give my radium results as uranium. Am I right?
If there is equilibrium, then you can use this nuclide or this nuclide for results of this and this. But if there is no equilibrium, then not.
No, what I'm asking is, I only measure radium-226.
Yeah.
So suppose I assume the equilibrium between all the radium.
Yes, if there is full equilibrium in the sample, full equilibrium, then each radionuclide has same activity. This is in the case of rocks, for example, but not necessarily in soil, plants, because there are biological effects, geological effects, very many different things. So equilibrium is very important. All right. Any comments? Yeah, I will go closer. Yeah.
Suppose I have to measure radium-226 in a soil sample, then the efficiency calibration will be done using a radium-220 source.
Not necessarily. Let's go back. So he asked about the efficiency calibration of radium-226. Where is that? Let's go here. So, how, if I understood correctly, his question is that how to do efficiency calibration for radium-226 for 186 peak, because there are two nuclides, uranium-235 and radium-226. So the idea is that these points here, they are measured points, but there is no radium nuclide in the original sample. We got this sample from NPL. It's a primary standard laboratory in Great Britain. So it's a primary laboratory. They know the activities of nuclides very well, and there is no radium in that sample. However, we can fit a curve here. 186 is close here. So, in determining the activity, we use that curve, not those points. If we calculate the activity by using this. So efficiency is strongly dependent on the energy. Is this the question that you wanted to know?
I consider the 609 peak of bismuth 214,
Sorry?
sir, if I consider the 609 kV peak of bismuth 214, then what should I do for the efficiency calibration part?
So, if you want to, it's a bismuth 214. Yeah. Bismuth has several peaks, which are located 2, 3, 4, 5, 6. They are located somewhere here. So then you use that efficiency of these energies. So you have to know the energy. Practically, activities are calculated by this. Too many slides. Practically, activities are calculated on the by using the software. Jenny, in your case. So you do not need to know the efficiency. The program should take the efficiency automatically into account. However, we should have correct curve for the sample in question. So this curve is valid only for this geometry. Beaker size like this, thickness like this, and there is practically water in that beaker. But I think that you will be, that Avanes will much more explain this point in laboratory session. Yeah.
So we do the same thing, extrapolation and then taking them.
Yeah. Yeah.
I think today you are going to do that. Yeah. Got it. Is there any other questions?
All right, I think that this is it. Please ask me later if you want.
Can you continue the afternoon session now? Because in the afternoon we can go directly to the laboratory sessions.
Just now you want?
Yes. So we still have 1 more hour to go before lunch.
All right.
So if you can take that.
Can we have a small break?
Yes.
Because talking is...
Biscuits are here.
yeah, I think there is something. Okay, this is enough. Let's have a 10 minutes break or so. Next presentation is very short. You can. How to open this? This way.
Yeah.
Oh, please. Thank you, Avanes, for the cookies.
It's your gift.
Please.
You
Yeah.
take.
Are they already taken? Yeah? All right, this is a scintillation thing, yeah. Yeah.
so that afternoon we can go directly to the lab session.
Yeah.
So we finish now. No need to come.
Right. This one. Yeah. I have to check what I want to show you some slides regarding scintillation spectrometry. This is only brief introduction to the lab session. At first, let's look at the scintillation materials, then liquid scintillation spectrometry. This liquid scintillation spectrometry, as told by Aria yesterday, it can be used by using beta spectrometry, but also for alpha detection too. All right, let's start with the scintillation materials. I yesterday talked something about these things. So, ionizing radiation interaction with scintillation material, this leads to a flash of light in the scintillation material. So this light is not necessarily visible in the human eye. And as I explained yesterday, the light interacts with the photocathode, resulting the produce of electrons, and these electrons are multiplied in the photomultiplier tube. The point is that the light signal is proportional to the activity of the radionuclide present in the sample material. This is sometimes very useful, this thing. I mean, the duration of the signal is usually very short. This is sometimes quite good in coincidence spectrometry. Okay, and because the signal is very short, the time resolution is also very good, much better than MCA's multi-channel analysis usually, or hybrid germanium usually has. But the point is that the energy resolution is not necessarily very good. But it can be applied in certain applications. So the point is that efficiency is sometimes very good because you can use very large scintillation detectors in some cases. So, scintillation materials are used to detect alphas, betas, and gammas. Alpha particles can be detected, for example, by placing a very thin zinc sulfide layer on the sample, which produces light and it can be amplified. So, scintillation materials can be grouped as follows: inorganic or organic scintillants, or gaseous, solid state, or liquid scintillant. This is an example of a surface contamination monitor. This is the photomultiplier tube. This. So, regarding inorganic scintillants, perhaps sodium iodine detector is the most commonly used scintillant for detecting gamma rays. This scintillant is used for beta particles, and these are used, for example, for neutron imaging or contamination monitor. And compared to the organic scintillants, light output is higher, but the response is slower. organic scintillants, it's a difficult thing. They are made compounds like plastics. The point is that the density at atomic numbers are lower compared to these, which means that they are not necessarily so efficient as inorganic scintillants. All right. This is a very short presentation. I am not expert in this area. However, if you ask me difficult questions, I hope that Aria or Parath will comment your questions. But these can detect low-range radiation like alphas and betas. If I understood it correctly, you are not using these spectrometers for alpha particles, only betas. All right. All right. So these are the nuclides that are usually analyzed by liquid scintillation method. You are mainly analyzing these. Do you analyze these? Tritium. Yeah. All right. So the point is also that the scintillation materials, they are selected based on the radionuclide to be analyzed. This is the Quantulus system. Do you have this coincident dual photomultiplier? Yeah.
The same. We have the same.
Similar. We have the same.
We have the same LSE.
Yeah. So, the point is that the sample is put into the scintillant material, and this is a good thing because it provides almost 4π geometry. So the efficiency is quite good for low energy photons or betas or alphas, because high energy gammas certainly escape from these small vials. So it's a cocktail, it's a mixture of solvent, surfactant and scintillators that produce light when excited by ionizing radiation. There are usually, or quite often, two different scintillants. First one releases the light and the second one enhances the signal. Do you use glass or plastic vials?
Yeah.
Polyethylene.
Yeah, all right. Yeah. So there is a quenching process which limits the applications. So the energy transfer from the decaying radionuclide, it is reduced or interrupted, leading to the decrease of produced photons. And this quenching process must be taken into account. There are at least two main processes. There are some others, I think, chemical quenching or color quenching. Are there some others too? Yeah. So this reduces total light output and shifts the pulse height spectrum towards lower energies. And this might reduce the counting efficiency too. Commercial systems are often operating in so-called coincidence mode, which means that the pulse is only registered if two photomultiplier tubes record the same pulse with within the short time period. This improves the accuracy and reliability of the measurements. For example, reducing the background noise or spurious signals. So you can detect alphas if you utilize pulse shape analysis. So it's possible to distinguish signals from alphas and betas. So these are alpha signals here. These are signals for betas. So alphas produce shorter and more intense light pulses, whereas pulses from betas, they are longer and less intense. There are ways to determine the so-called PSA level by using, for example, standard samples such as this nuclide or this nuclide. Only these two. But what is the reason why you are not using alpha detection in?
Alpha spectrometer HPG
So-
for gamma.
Yeah, all right.
Basically,
So whichever is not possible
possible-
for using HPG
Yeah.
and alpha spectrometry,
Yeah,
you do it.
and that is a laborious process.
yeah, yeah.
For liquid
Yeah,
simulation,
it
the process is laborious.
It is, yeah.
Again, the cocktails are that simulators.
Scintillator cocktails are quite expensive.
Yeah, yeah,
So
they are.
in order to analyze polonium,
Yeah,
if you use the digestion method,
Yeah.
it is not that costly. But if you have to use the liquid scintillation counter,
Yeah.
then
very expensive.
it is very expensive.
yeah, yeah. I think we have 3 or 4 these Quantulus systems in my laboratory, as you saw in the video. We are routinely analyzing polonium, for example.
So I had a question. If you are analyzing alpha using liquid scintillation counters, wouldn't there be a problem of attenuation due to the vials? Because alphas are not that penetrative enough.
Well, you can ask Aria.
Vials, but you are changing the vial.
The plastic might attenuate.
Yeah, but we are not reusing that.
Hmm.
For each sample, you have to use the new one.
No. Okay, plastic might attenuate the polonium, right? So I don't know how you use.
Mm. I don't have special experience in
No,
this
we can skip
area.
the question.
Yeah.
For the next one.
Yeah, all right. So, about the scintillation spectrum analysis, I mean that I would like to compare. I'm not considering here not liquid scintillation systems, only those solid systems. So basically, the spectrum analysis is same for high purity germanium. There are no big differences, except, of course, the resolution, which is not very good. For example, in sodium iodine detectors, the resolution is 7 to 9% or something like that. So, and resolution is calculated like this. So it's a big difference, so energy difference of the left side and right side divided by the energy. And the problem is that peak overlapping may be notable. So there is comparison for iodine, sodium iodine and high purity germanium. So there is a big difference in resolution. I think using scintillation materials is a very good system in those cases when you detect for example, only one nuclide such as cesium-137. And there are different type of materials. I think this is bismuth, germanium, oxygen material, this one. This is lanthanum bromide. The resolution is very good in that type of the scintillator. But these are quite expensive, these lanthanum bromide detectors, compared to the sodium iodine detectors. This is one example. Basically, detection system is like high purity germanium. You can have a lead shield here, you can put the sample here, and this kind of system can be used in the field measurements. But then you have to take into account that if temperature varies a lot, which is not a problem here, but a problem in Finland, if we want to measure or use this system during winter time or summertime. All right, this is the energy calibration curve, which is quite linear in case of sodium iodine. This is one example of sodium iodine spectrum for cobalt-60. There are same kind of peaks as in high resolution gamma ray spectrometry. One of you asked me why there is only one backscatter peak when there are two gamma peaks. But the point is that backscattering peak is not very much it doesn't depend very much on the energy. It depends a little bit, but not very much. That's why this peak is more wide. All right, I think, okay, this is almost the final slide. So I didn't look through this paper, but perhaps you might look through, because they say that there are some new ways to do scintillation spectrometry for environmental sample measurements. I think this is my last slide. So, advantage of scintillation spectrometers is that they are or can be very large. I remember that Finnish Geological Institute used a very big scintillation detector after the Chernobyl accident. They put that detector in an airplane and use very low altitudes, 100 meters or so. The detector size was indeed very big, and the resolution is very bad. But they just wanted to produce a fallout map in Finland, mainly from cesium-137. So, advantages of cesium is that they are cheaper compared to high purity germanium by a factor of at least 10, at least. They are appropriate in field measurements. You cannot carry heavy lead shields out of the laboratory. They need low power, no cooling. Maintenance is simple, relatively simple. Application areas are quite wide. They can be well suited, for example, in security systems such as portal monitors like this one here. And once more, the efficiency is good. For example, these are the portal monitors looking for this big truck here. All right, this is it. No more. And the timing is okay. Is it time for the lunch or do you have any questions? If you ask, please contact Ari or Bharat. Bharat is not here. All right.
Thank you, sir.
Thank you very much. Shall we go to lunch or no?
Yeah.
Yeah.
We can take just 2 minutes.
Yeah.
Sometimes there's no one else who loves me like you used to. Sometimes we're not ourselves. There's no one I can turn to. And I know all the feelings that we shared are in the past. And I know your relationships are never meant to last. And I'll take some time, but I'll be alright. We're moving on. We're moving on. I know times are tough, but I've had enough.
start ratio.
ಫಸ್ಟ್ ಹೋಲು ಎಕ್ಸ್ಪ್ಲೇನ್ ಇರಾರ ಬರ್ತಾರ ಯೋಜಿಸಿರ లైట్ పూర ఆన్ ఉండదు
ಇಲ್ಲಿ ಜನ ಕಡಿಮೆ ಇದಾರಲ್ಲ, ಅಲ್ಲಿ 2 ಬ್ಯಾಚ್ ಅಲ್ಲಿ ಹೋಗಿರೋದು. ಬಟ್ ಇಲ್ಲಿ ತುಂಬಾ ಕಡಿಮೆ ಇದ್ದಾರೆ. ಅಲ್ಲಿ ಇನ್ನೂ ತುಂಬಾ ಜಾಸ್ತಿ ಉಂಟಲ್ಲ, ಒಂದು ಡಿಸ್ಟ್ರಿಬ್ಯೂಟ್ ಮಾಡೋಣ. ಒಂದು 4 ಜನ ಇಲ್ಲಿ ಬರ್ಲಿಕ್ಕೆ ನೀವು ಹೋಗಿ. ಬಿಕಾಸ್ ಅಲ್ಲ ದೇ ಆರ್ ನಾಟ್ ಸ್ಟಾರ್ಟೆಡ್. ಬಿಕಾಸ್ ಈ ಬ್ಯಾಚ್ ತುಂಬಾ ಕಡಿಮೆ ಇತ್ತು. 4 ಜನ ಬರೋದಾದ್ರೆ ಬೇಗ ಹೋಗ್ಬೇಕು. ಹೋಗಿ ಏನ್ ಮೇಡಮ್? ವಾಟ್ ಮೇಡಮ್? That's why we talk in Kannada. What we talk in confidential. ಯಾರು ಹೋಗಿದ್ದಾರೆ? Let's wait for 2 minutes if they are joining. So what we are doing today here is, preparation of sample for alpha spectrometry. Okay. So this is one of the extremely important step. If you want to get, correct result, reliable result, this spectrometry, preparation of the sample for spectrometry is very important. Okay. So we will show you, of course, each one of these steps takes about 24 hours to complete. So that's why we can't show you the starting from the raw sample to this is the end stage. So that's why we have kept the samples in various stages so that we can see that. If you wish, any of you want to wish to do this by yourself, you are most welcome. We will give the sample. Starting from the point, step number 1, adding the chemicals. You do that, you digest the sample, you convert it into hydrochloric acid medium, and then do the plating. There, plating is going on. Okay, and then prepare the sample like this. This is the the clean silver case, because polonium deposits on silver. Okay, so that's why we use silver. So you can prepare the sample, or we call it plating of chemical deposition of polonium on silver. This is sorry for disturbing, because the strength is very, there are only few. Okay. So some of you can come this side. So what we are demonstrating today is how to do prepare the sample for alpha spectrometry. So for demonstrating that, I have taken a soil sample. You see, this is a raw sample. We get the sample from the field. So now I have taken the soil sample. It could be a sediment sample, or it could be a sample from a biological, so for example, fish sample, or it could be, a vegetable sample. What we should do is, get the sample from the field, dry it at 110 degree to remove all the water content in it. How much to dry? So you have to dry it at least 24 hours and weigh it again and again, and the mass of that should be constant. Every time the weight you should get should be constant value. That shows that all the water has gone out. Okay. So this is a dried sample like that.
Save the sample.
Huh?
Saved.
Yeah, dried and sieved. Yeah. It is not mandatory that you sieve, it depends on your applications. For example, certain applications like, for example, those who have come from nuclear facilities, they want to do the dose assessment study. In that case, they don't prefer to sieve it, because if you sieve and take out your fraction, that fraction may contain higher activity.
So they will be inferring higher dose. Okay. Whereas some of your application, like earth science or sedimentation rate measurement, it may require a certain fraction of the soil to be analyzed. Okay, in such cases you can do the sieving. It is depends on the application. Here I think we have sieved sample. So we have taken a sieved sample, and this sieved sample of soil we have to subject it to complete digestion. It is a destructive technique. Gamma spectrometry is a non-destructive technique. So here we digest the sample completely. How do you digest? We add strong acid, nitric acid, perchloric acid mixture, or nitric acid, hydrogen peroxide, and the digestion can be open air digestion or it could be microwave digestion. You can see the microwave digestions also in the next room. We normally do the microwave digestion because there is no loss of sample at the time of during this digestion process. You may often see that when you do the digestion in the open air in a hot plate, there will be spurting. When there is a spurting, there is a sample lost. Whereas in the microwave digestion, it is digested at 100 bar and there is nothing going out. Okay, so you get better recovery there. But there are advantages and disadvantages. Here in the open air digestion, you may take 10 gram of sample, you may take 20 gram of sample, but in the microwave digestion, in one Teflon bomb, you can take maximum 0.5 gram. So if you have 10 bombs, so you could get maximum 5 gram or even less than that. So it depends what exactly your application is. So if you want to study the trace elements and if you want to subject the sample for for example ICP-MS, then microwave digestion is always better because you want to avoid cross contamination. You keep 3 samples in the hot plate, okay, and you are digesting, and when it spurts, a portion of this may fall on the other. So such cross contamination you want to avoid. So that's the reason you go for microwave digestion. We will show, if you are interested, we will do one microwave digestion here tomorrow or day after. It is depending on your interest. So basically it is a total destruction of the sample. So whatever organic matter is there, carbon content is there, should be digested, should come into solution. So that is, for that we use strong acid, nitric acid, hydrogen peroxide mixture, or nitric acid plus perchloric acid, or if you want to digest the silica also present in that, then you go for HF. You take instead of glass beaker, you take Teflon beaker. Take a Teflon beaker, and Teflon beaker untalla ಇಲ್ಲಿ ತಗೊಳ್ಳಿ ಒಂದು ಇಲ್ಲೇ ಉಂಟಲ್ಲ ಅದು ಆ 10 ಎಕ್ಸ್ಟ್ರಾ ಇರೋದು ಎಲ್ಲ ಅಲ್ಲೇ ಉಂಟಾ. You can take Teflon beaker also if you want to use hydrogen HF, hydrogen fluoride, because that is reactive to the glass. Okay, so that is the basic thing. So this is the raw sample. In this sample I have already added nitric acid. So, and now you after you add nitric acid, you also put some hydrogen peroxide and you heat it. And this is the Teflon beaker, you see. So you should use Teflon beaker if you want to use HF. Okay. So you heat it and then add that acid mixture again and continue that process maybe about 5 times, 6 times. Then you will see that all the organic matter gets destroyed and you get a clear solution like this. Okay. So from here it should come here. Okay. Okay. You digest with nitric acid and perchloric acid or hydrogen peroxide or HF, whatever it may be, and then all the carbon organic matter will be destroyed. The elements which are there in the sample will come to the solution. Okay. Now it is in nitric acid medium, is it not? But for the silver, for depositing, the polonium onto the silver disc, we want it in hydrochloric acid, because nitric acid reacts with the silver. If you put silver into the HNO3 solution, within a minute it will disappear. Okay. So, we do not want this sample to be in nitric acid medium, we want that to be in hydrochloric form. So, what we do, once you digest the sample, then you convert into HCl medium, 0.5 normal HCl medium or 1 normal HCl medium. How you do? Nitric acid was there, you evaporate it, add concentrating nitric acid twice, then you add 0.5 normal HCl, 100 ml or 2 ml. ಈಗ ಎಷ್ಟಿದೆಮ್ಮ 100 ml ಇದೆಯಾ ಅದು? 75 ml, whatever the volume you want. Okay. So, now from this stage it has come to this, and intermediate stage is there when it was digesting, and then from there I have converted into this stage. This is in hydrochloric form, 0.5 normal hydrochloric form, and this is the one set of sample, soil sample, and this you see the clear sample is phosphogypsum sample. There are two varieties of samples we have taken. These are all soil samples, digested. You get yellow color because there are many other organic elements, iron, ferric form it is present. Here it is phosphogypsum where there was no iron. So, hence you will find that it is a clear. Okay. Whenever there is a higher organic matter content, you will get higher, greater color, dark color. So, there was, these are the organic rich samples. These samples, phosphogypsum is a white powder, there was no organic material in it. So, these are samples with no organic material. So, that is the difference. So, you may ask why there is a yellow color here, white color, because it depends on the sample, which sample it is. So, these are soil samples, these are phosphogypsum sample. Is it clear to you? Now, it is in 0.5 normal HCl medium, right? Right. Now, there is polonium, whatever polonium is here has gone into the solution, or whatever any other element which are there here. Okay. Now, this sample, this is the basic sample preparation. This sample you could take it through ICP-MS also if you want to determine the iron, nickel, copper, or manganese, magnesium, zinc, copper, whatever you want to do, you can subject the same thing to ICP-MS, or you can subject it to AS determination, whatever may be, So, depending on your instrument. These are the basic step the common step for any elemental determination in a sample.
Can I use those sample in LSC?
Huh?
Can I use those sample in liquid scintillation?
This one?
Yes.
Liquid scintillation, this sample should be miscible with your cocktail scintillator. Okay. If this is miscible with the cocktail, then you could use. Is it not, Arya? Yes. If it is not miscible, it's not. Yes.
Sir, at what stage we are adding polonium to both lines, sir?
Yes, we are adding that. So, I am coming to back to that.
One more question. How much time will it take for the digestion?
It depends on the quantity of mass of the sample you take. If you take, say, for example, 1 gram of sample, this digestion will be over by 24 hours in open air. And the same thing in the microwave digestion, this takes about 1 hour. Okay. But then I said there are, advantages and disadvantages. It depends on your application. If it is for only polonium determination, I would rather go for open digestion, because I can take larger mass of the sample. If I want to go for ICP-MS, then I go for this microwave digestion, because there I need microgram of sample and I need minimal cross contamination. That's the thing, right? Any doubt before that? Yeah. Now, one important step we missed in the beginning itself, before we added this concentrated acid, is to add the tracer, polonium 209 tracer. Why tracer has to be added?
To determine the efficiency of the.
Yeah, to get the efficiency. Polonium 209 or polonium 210, 210, they both chemically both are same. Okay, it's only the one mass missing there. One is 209, other one is 2010. Both follow the chemical procedure. So, in order to determine what is the recovery of your polonium 210 of your method, we need to add a known activity of PO9, polonium 219. Or the other alternative is you should take a reference material. IAEA gives polonium 210 reference material. You could digest a reference material and find out what is the recovery. But there also there is a problem. See, in one, if you determine the efficient recovery, in one method, for one trial you may get 90%, for other method you may get 80%, the third one you may get 84%, and the fourth one you get 86%. There is always an error, is it not? Error in the measure, starting from the weighing of the sample and till the end measurement, taking the counts from the spectrum, there is always uncertainty associated. There are 4 or 5 important uncertainties. One is weighing, other one is recovery associated with that, and the third one is counting error involved in it. So, if you determine the efficiency for one sample, say for example, in a month I am analyzing 100 samples. Okay, today is December 10th, and till December 30 I am going to analyze another 100 samples. And you may ask, no, I take one reference material today and I determine the efficiency. But today you get that efficiency, 90% you may get. Tomorrow you take another batch of sample and the recovery in that can be only 84%. Same, it could be. It depends on, how long you digest and how long you plate, all those things. No method will give you exact value 90%. If you say 90%, no method will give you 90% in 100 analysis. You do 100 consecutive analysis, no method will give you 90%. It will vary, and sometimes you may vary by 10%, 15%, we don't know, depending on the sample. It depends on the sample also. So, best thing is to do in spectrometry is you add tracer for each and every sample, okay, so that you determine the recovery and efficiency for every sample. So, that gives you the exact value of the activity present. So, in the beginning itself, what we do for the dry sample, we add tracer. We have tracer here, which is polonium 219 spike we call. So, this has a known activity. I think it has got 4.5 dpm. I will give you the exact value of this. I think 4.5 or 4.8 dpm. So, we add 1 ml of this to this. Okay, 1 ml of this to this. Rashmi, 1 ml add ಮಾಡ್ತೀರಾ? ಯಾರು ಆಗ್ಬೋದು, Rashmi or Bharat. But it is always important to note down. Normally, when I was a student in a BSc, my teacher said you add accurately pipetted out 1 ml of sample. Okay. At that time, it was okay. We used to do very methodically. 1 ml is 1 ml. You used to be, but we don't know. But when it comes to very low detection level thing, you think that it is a 1 ml pipette. Okay. It could be 0.9, or it depends on the user. There could be a drop at the tip which may not have fallen onto that. Okay. Or you see the meniscus, for example. You may see like this, you may see like this. There could be different. So, it is always better, of course, you pipette out exactly, but it is always better to add the tracer on mass basis. So, what you do is you measure this in an electronic weight balance. Rashmi, Arya, take this and weigh the sample.
If
Huh? So it is always advisable, or it is always advised to add the tracer, or not only tracer, any sample you want to take for analysis on mass basis, not on volume basis, because volume basis there is larger uncertainty associated with that. So you can see that how they do it. So error associated in mass based measurement is minimal compared to volume based. ಇದು ದೊಡ್ಡ ದೊಡ್ಡ ಆಗ್ತಾ ಹೋಗ್ತಾ ಉಂಟಲ್ಲ, IRPಗಿಂತ ಮೊದಲು ಅದು ರಿಪೇರಿ ಮಾಡಿಸ್ಬಿಡು. IRPಗಿಂತ ಮೊದಲು ಹೊರಗಡೆ ಒಂದು ಪೇಂಟ್ ಎಲ್ಲ ಮಾಡಿಸಿ ಒಳಗಡೆ IRP ಆದ ನಂತರ ಪೇಂಟ್ ಮಾಡಿಸುವ. So you see that they are adding 1 ml of tracer, polonium 209 tracer, which has a half-life of about 122 plus or minus 5 years. So you note down that, close madam amele. Aita. You,
Standard purchased from?
huh?
Standard purchased from?
That is brought from USA. Yeah. So these standards are available. Yeah, you can get Amersham, or you could get Amersham, or no, there are many other companies. Yeah, we bought it from USA, and you can go for either NIST or Amersham, or there are few other French companies which gives its radionuclide standards. So this is very important. So you could add 1 ml, but then that 1 ml need not be 1 ml. It depends on the how accurate your pipette system is, how accurate that pipetted out goes into the sample. But this is the most accurate method where you can minimize the uncertainty associated with it. So we have added tracer now. Now do this sample we have to add concentrated nitric acid and perchloric acid mixture. Okay, that is what you see here. Okay, right. So these samples which we have here, out of that 10, 8 or how many are there? 9. 9 out of 9, 7 have tracer plus polonium, 2 have only polonium, no tracer. So we wanted to demonstrate both of them. With tracer how the spectrum looks, and without tracer how the spectrum appear in the alpha spectrometer. So from this tracer plus sample, it has gone to this stage, then digested and converted into hydrochloric acid medium. These steps are very much clearly mentioned in the manual, is it not? Yeah. Now where are we in this manual? Yeah. We are here. We are here. 7. Yeah. We are at step number 7. Any doubt till this point? Correct? Now, what is the next step now? Yeah, that's what we see here now. You see? Rashmi, one sample and plating it video already. Now, meanwhile, what you should do, before the samples go for plating, what we should insert that is inside is this silver disc, okay, because polonium reacts with silver here and forms silver chloride and deposits on that chemical deposition. So here what you should you should take a silver disc. You can see here we have silver discs, many of them. These silver discs should be cleaned properly and polished and should be background counted. If you are using the silver disc again and same disc again and again, so you should put it into chromic acid. If you put the silver disc, once plated silver disc onto the chromic acid, then whatever plated polonium is there will come to the solution. So this will remove, or this chromic acid will remove all the polonium there. Then you have to polish it and then clean it with the double distilled water and ethyl alcohol, and you have to dry like this. Okay, these are the silver planchets which are ready to take for plating. And before we take it for plating, this ಏನು ಮಾಡಿದ್ರಿ ಒಂದನ್ನು ನಂಬರ್ ಬರಬೇಕು, ಗಮ್ ಟೇಪ್ ಹಾಕಬೇಕು. See this, when I place the silver disc onto this, the polonium which is there in the sample will present in all the sides of the disc. There are two main sides, up and down. If I place it like this, there will be one bottom side, one in top side. Polonium will deposit wherever silver is there. So we don't want, because alpha spectrometry is performed only in one side. Otherwise what you should do is, you should count it on both sides, side A and side B, okay. And we don't want, because alpha spectrometry often takes weeks together, very low activity samples in sedimentation studies. You may have to count it for 200,000 seconds, okay, and you repeat it for one sample, it is 400,000 seconds. We don't want, we want to count only in one side. So for that what we do is, you see here, on one side they are putting polythene tape on the bottom side. See, they will show you, because I have not put gloves, that's why they are handling it. See, one side they are putting polythene tape.
The number size we are putting.
Yeah. ಅದು ಸಿಕ್ತಮ್ಮ ಎಲೆಕ್ಟ್ರೋಪ್ಲೇಟಿಂಗ್ ನೆಟ್ ಇಲ್ವಾ? ಇಲ್ಲಿಟ್ರಿ ಹಾಗಾದ್ರೆ ಇರ್ಬೋದು, ಎಲ್ಲೆಲ್ಲೋ ಒಂದ್ಸಲ ಎಲ್ಲ ಕ್ಲೀನ್ ಮಾಡ್ಬೇಕಮ್ಮ. ಒಂದ್ಸಲ ಕ್ಲೀನ್ ಮಾಡ್ಬೇಕು ಅದನ್ನು ಫುಲ್. ಇರ್ಬೋದು, ಇಲ್ಲೆಲ್ಲೋ ಇರ್ಬೋದು. ಇದನ್ನು ತೆಗೆದ್ರೆ ಖಂಡಿತ ಸಿಗ್ತದೆ. ಅದೆಲ್ಲ ಎಂತ ಬುಕ್,
ಅದಕ್ಕೆ ಓಲ್ಡ್ ಸ್ಯಾಂಪಲ್
ಅದೆಲ್ಲ ತೆಗಿಬೇಕು, ಎಲ್ಲ ತೆಗಿಬೇಕು ಅದನ್ನು. Okay, see, she has now pasted the polythene tape on one side. So because of that, now the polonium will not deposit on the other side. Okay, so now the plating which is going on there also we have put what is called gum tape.
One doubt, if maybe there is a stupid mistake, doubt, so that plastic will
not, it will not, it is plastic will not react with the sample.
Okay.
It is very stable. Okay, and then we have to put the sample number, everything.
It's an acid maybe, no? Now it is
Nothing happens to the plastic. Polyethylene is very,
resistant to
we can withstand very strong acid. That's why you store acids in some of the plastic containers, even yeah, like that. So she has prepared the planchet now. You mark it, whatever it may be, way you want. You put your sample name, and now we go for plating. Yeah. So now you see, when we go for plating, there is one more important step involved here. You see that, I said, this is the phosphogypsum sample, this is the soil sample. Soil sample, there is, iron is the most abundant sample, is it? Abundant element in the universe. So there is iron which is in the ferric form. Okay, that ferric form will intervene with the silver plating, this polonium plating. Along with the polonium, iron will also deposit. Then what will happen? Your silver disc will turn out black. Okay, there will be iron coating. So if you have iron coating also with the polonium, that will give you distorted spectra. Spectrum will not be clean. You should always get a very clean peak. So we don't want that, distorted spectra, and for that we want to reduce the ferric ions into ferrous form. Okay, for that what we do is we add ascorbic acid. Yeah. So first we put a magnetic bead like this. So we put a bead stirrer, magnetic stirrer. So whenever you do the radiochemical analysis, it is extremely important to ensure that each and every step you do should be very clean, because there is always a possibility of cross contamination, because you are measuring extremely low levels. A small contamination will give you result bias 50%. Okay, so we should always avoid that. I'll rotate Madi first. Slow. And you rotate it slowly, you see, magnetic bead. Now she will put ascorbic acid, and you ferric will reduce into, yeah.
How much quantity, sir?
That you will see when it stirs, you should get a colorless solution. Yeah, that yellow color will go. You see that it is now become, yeah, you see, almost colorless. You can see that.
So in phosphogypsum sample we don't need to add ascorbic acid.
Pardon?
In phosphogypsum sample we don't.
We always add, because even if there is some iron content, ferric form, that should be reduced. It is not that it is clean, there is no minimal iron, but even we want to avoid all those things. You see now all of them has, all color has gone. She will add some more on the half speed way kanta. Dissolve ugly. Let it dissolve.
So one question that is, why are we keeping this phosphogypsum sample?
To demonstrate you some spectrum, that's all.
No, means one is sample and another is phosphogypsum.
This is also sample. This is soil sample. This is phosphogypsum. Both are samples. I am giving you two varieties of samples. Or if you wish, you can get some leaves from outside and bring it. No problem.
So I was thinking,
Or you
does
can
it
go to
have
market
any
and get some fish sample. We can do that. So there will be, instead of two, now there will be one leaf sample, one fish sample.
So what is the thickness of that silver disc? Thickness of that silver disc?
Silver disc thickness, I think, few fraction of a millimeter. We give the dimension of all those things. Yeah. So silver disc dimension is not a big deal, the issue, because you could prepare slightly bigger, because every time you polish, a layer goes off. Yeah. So if you have a plan to use the same disc again and again, but of course, if you use it for high activity measurement, it is always advisable not to use it again, because in every plating the background will go, one or two counts increase you will find. So it is always better not to go for use a silver disc which is used for active samples. But for normal background samples, you can always, in that case, even if the sample is the silver disc is thick, there is no issue. Plating is only on the top. So it all depends on what is the thickness of the plated sample. That is the important thing. That sample, plated sample should not be thick, because alpha can be very easily stopped. Okay, that's why we want to avoid the iron, other cross interfering element. Previously we used to do it at 95 degrees centigrade. This then if it is 95 degrees centigrade, the efficiency of plating is higher. Say you get about 95%. But here you may get efficiency of about 70–80% depending on the sample. But then this gives you a much cleaner sample, prepared sample. You will at the end of the day, see this sample plating was going on for 24 hours almost. So you see that silver disc as good as new one. Whereas if it were to be in the 95 degree temperature, many other elements would have sampled, that would have given a black color. In that case, that source preparation is not good enough. That you get the spectrum distorted. You see, now it is almost all color is gone now. Slightly some color is remaining. That is not issue. Now she will introduce the silver disc. Yeah, only this face which has been pasted with the gum tape should go down, and the other one should face up. That's all.
ಅನಸ್ವರ ಮತ್ತೆ ಪೇರೆಂಟ್ ಬಂದಿರುತ್ತೆ.
ಯಾರು?
ಅನಸ್ವರ ಲಾಸ್ಟ್ ಇಯರ್ ಸೆಕೆಂಡ್ ಇಯರ್ ಸ್ಟೂಡೆಂಟ್ ಬಿಟ್ಟು ಮಿಡ್ಲಲ್ಲಿ ಸೆಕೆಂಡ್ ಇಯರ್ ಮೆಡಿಕಲ್ ಫೀಸ್ ಸ್ಟೂಡೆಂಟ್ ಬಿಟ್ಟು ಹುಷಾರಿಲ್ಲ ಅಂದ್ರೆ ಹುಷಾರಿಲ್ಲ ಅಂತ ಕೇರಳದ ಅನಸ್ವರ ತುಂಬ ಸಲ ಕಾಲೇಜ್
ಬಂದಿರ್ ಮಾಸ್ಕ್ ಕಟ್ಕೊಂಡು ಹೋಗ್ಲಿಕ್ಕೆ ಅಂದ್ರೆ
ಅಲ್ಲೇ ಕೆಳಗಿದ್ರೆ ತೆಗಿಬೇಕಂತ ಕೇಳಿ
ಮಾಸ್ಕ್ ಕಟ್ಕೊಂಡು ಹೋಗ್ಲಿಕ್ಕೆ ಅಷ್ಟೇ. ಆಯ್ತಮ್ಮ? ಉಲ್ಟಾಯ್ತಾ? They are expert. Yeah, they are trained, thoroughly. And ಸ್ವಲ್ಪ slow ಮಾಡಮ್ಮ. And that bead should rotate very slowly. So this sample we have kept now, we are preparing today. Tomorrow, today exactly you have to note down the time, because for all the samples you should note down when the sample was collected, okay, when the sample was taken for digestion, that is important, and when the sample was plated. Now the date hakama, date matte time, because if you count this sample, this same planchet, say for example after 1 month, considerable amount of polonium might decay. So you have to do a decay correction. That's what Dr. Roy was telling. You saw decay correction. You were showing the graph, no? So you should do the decay correction for that. ಅದಕ್ಕೆ ಡೇಟ್ ಮತ್ತು ಟೈಮ್ ಹಾಕಮ್ಮ. ಹಾಕಿದ್ರಾ? ಡೇಟ್ ಟು ಟೈಮ್ ಬರೆದ್ಬಿಡಿ, ಅವ್ರಿಗೆ ತೋರಿಸ್ಬೇಕಲ್ಲ ಕರೆಕ್ಟ್. So ಒಂದೀಗ ಅಲ್ಲಿ ತಗೊಂಡಿದ್ದೀರಲ್ಲ? Okay. This was plating was going on since yesterday evening. So this 24-hour will complete today around 5:30. Today at 5:30 we will take out this. We will put it for alpha spectrometry. This needs another 24 hours. This will be ready for counting tomorrow at same time. So tomorrow we will remove this and we will put it for alpha spectrometry. And one sample which is already finished has gone there for alpha spectrometry. That will serve for your demonstration for you today. This will serve for the demonstration for tomorrow's batch. This will for day after batch. Okay? 48. And meanwhile they will be plating the other 2 samples also with the tracer and without tracer. Suppose if you want to do the measurement, there is another, I said, one is spectrometry, other one is bulk counting using zinc sulfide counting system. If you add tracer and already existing polymer, then will you be able to count it with the bulk counter? Yeah. So the counts you get will be from both.
That is a gross counting.
Yeah, gross counting, because it gives counts from both. It doesn't distinguish between isotopes. Whatever alpha is there, it will give you. So you will not be able to get the efficiency. Okay. So that's why spectrometry is advantageous. You could, in one sample, you add the tracer, you get the recovery and the counting efficiency for that particular sample. That is the advantage if you add tracer. Okay, is it clear? Yeah. Any questions on this so far? If there is no questions, we go for spectrometry now. What is the time now? Tea ready there? Tea kudidu hogodu. Any doubt? Any questions? ನೀವು ಅದು ಇಲ್ಲ ಅಂದ್ರೆ ಕೆಳಗೆ ಆಲ್ಫಾ ಸ್ಪೆಕ್ಟ್ರೋಮೆಟ್ರಿಗೆ ಹೋಗಿ ಇದು ತೆಗಿಬೇಕಲ್ಲ. ಎಂತದು 24 hours.
ಸರ್ 48 ಅಂದ್ರಲ್ಲ ಸರ್
24 hours.
ಈಗ 48 ಅವರ್ಸ್ ಅಂದ್ರಲ್ಲ ಸರ್ ಅದು
48 hours ಇಲ್ಲ 24 hours. Did I say 48 hours? No, 24 hours. 24 hours.
After 24 hours,
You will be removing this.
and
And it is expected that after 24 hours, this plating will be complete. Yeah. So you may get about 75 to 80% of plating.
Okay.
So it is optimized.
In another way we can do. So
Pardon?
in our lab we are doing like that. We are increasing the concentration with the operation.
That's what I am telling you. You heat it at 95 degree.
Okay.
You do it plating at in a hot condition. Plating at room temperature.
room temperature
This is the reason I am telling. If you do the plating in 95 degree,
instructions
then you at the end you see that the plate is black.
Yes, completely burned.
Yeah, yeah. So then your spectrum will be you will not get a clean spectrum. Here you see here in the spectrum, you can come here see. This is now plating is going on for 24 hours. Even now the planchet is as good as.
Because of the color it will not be the problem.
Color there will be problem because that black color is also a coating. You will see the resolution difference between this and other numbers. Definitely there will be difference.
In our lab we are following that.
Okay.
Petroleum on that.
Yeah. That is electroplating.
Electroplating.
That is electroplating.
Yes,
Yeah. This is normal chemical deposition. Electroplating, there is a electroplating unit separate. I show it to you tomorrow. There is a electroplating unit where you take the sample, on the bottom you fix the disc and you put sample over that and you supply voltage. So that is electroplating. This is chemical deposition. There is also two methods. One is the normal chemical deposition method and the other one is electroplating.
following, we are following this.
Same. This is enough. Yeah. If you want to do uranium thorium analysis, and then your disc will be either stainless steel or nickel. Yeah.
Stainless steel or nickel.
Nickel. Yeah, it depends on the element which you are analyzing. For some elements it is nickel, some elements it is stainless steel. For polonium it is silver. Right. And you could also use platinum dish. Yeah. But for all electroplating, you should always use platinum electrode. We have platinum electrode as well as this plating unit. They will locate it today. We'll get it tomorrow. Okay. So this is the one main difference we are following. Plating in room condition because this gives much better spectrum. Okay. Okay. Huh? Yeah. I said, I demonstrated the polonium because in alpha spectrometry, that is the easiest radium to be subject for radiochemical analysis and then do the alpha spectrometry. Because if you take uranium and thorium, the sample preparation itself takes 3 to 4 days. You have to pass it through anion, cation exchange column. That is all you need is a column, Dow's column. That's all. We could do it, but nowadays we don't do it because majority of those work are done with gamma spectrum. With uranium, you can use 1001 protective thing, or 93.5 you think, and like that. And thorium, of course, you can do directly through actinium. Right? So if there is no doubt, we go down, and meanwhile on the way we see this micro diagram. Rotor alone,
makes this clean, we open the detector, keep the sample inside and close it and lock it. So this opening is not done, we don't keep it open for not more than like unnecessarily. As soon as it is done, we have to close it. So no dust that enters here. So that is the same reason why we are wearing this footwear. The we don't allow outside footwear to come in. So this much is clear, right? Clean. Filter or this clean room. It's not really necessary, but again, it's expensive. Can do. So suppose we want to do that. So this is, see, even if there is a dust inside, you will get a spectrum. While background correction, why we are doing background correction? To eradicate these kind of problems. So we can remove those interferences. But again, we don't want that interferences to go inside at all. So that is why we are doing this. Okay.
You can remove.
Yeah, by background correction. So then your minimum detection activity will go up. So that what happens is that suppose if you are giving me a sediment sample,
But the
which
background is taken well ahead, right?
no, that is why we have to take background every 15 days or every 1 month. So you can't do background once in a while in that case. Okay, background correction, background once in a while is very important in that case. Okay, so I hope I have sorted your doubts. And again, what will happen? Suppose background is high, you have your samples are very small, 5 grams. The ocean core samples sometimes we get it is like 5 gram or 10 gram. Now I keep the same sample inside. My MDA formula depends upon efficiency, activity, weight. Weight is less, so MDA goes up, and then you have time. Okay, so lower the weight, my minimum detectable activity goes up. So that is why I have to keep and it is directly proportional to the background counts. So lower the background counts, lower the MDA, but lower the weight, higher the MDA. So for all these kind of samples, we have to keep background as low as possible. Okay, I hope I'm clear now. Yes. Okay, now the sample is kept inside. I will again do the same thing as I did over there. Detector 1, clear the sample and start counting. So now counting time I have given here is over 60,000 seconds. Okay, but you can see why I have given so much. So let us wait till 100 seconds. Okay, and see how the spectrum is forming. See, it's around 30 seconds. Can you see any kind of peaks here? Close. Can you see any kind of peaks now? 30 seconds. Yes, uranium source. This one is called as RGU. It's an IAEA, International Atomic Energy Agency certified reference material. It is supplied from them, and it was done in. So the spectrum.
They should handle themselves.
Yes, sir. I'm just showing them first, and then I'll give the spectrum to them. Yeah. So you can see that even for almost 69 seconds, I cannot get any kind of spectrum, right? There is one peak over here, small peak, but this is an source. If you have your sample, you will get still a flat line. So that is why we have to keep for longer counting. So 30,000. So if you don't get a peak at 30,000, what do you do? We increase the time, 60,000. If you don't get a peak for 60,000, try more. If you are sure it is there. If it is not there, what? Which one? No. It does not depend. It depends upon the concentration of the radionuclide in your sample. Okay. Suppose if the radionuclide concentration is high in your sample, you can keep lower the time. Yeah. Okay. ಓಕೆ ಅವ್ರ ಹತ್ರ ಕೇಳಿದೆ, ಅವ್ರು ಅಲ್ಲೇ ನಿಲ್ತಾರೆ ಹೇಳಿದ್ರು.
ಇಲ್ಲ 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 ಅವರೊಂದು 2 ಡೌಟ್ ಹೇಳಿದ್ರು. ಓಕೆ ಸೊ yeah, where was I?
So it depends on concentration.
Yeah, it depends upon the concentration of.
That fixing is depend on what, like you were.
See, I think sir can answer that. You want to answer it? He is asking, how do I know how much time should I count for? For unknown sample.
How the counting time is fixed?
Before using gamma ray spectrometry, you can use, for example, Geiger counters to check the overall activity.
Yes.
That's one point. But typically, environmental samples they contain
Very low.
very low amounts of radionuclides, so the measurement time should be quite long.
Quite low. So you start with, like, let us say you start with 30,000 seconds. You don't get peak. Increase the time. 60,000 seconds.
Generally, see, for example, if you don't have any fixed time. Suppose
See,
60,000 seconds you have.
Yeah.
And if anything you are not getting, we will be again counting it for much
No,
more
no,
time.
no. We will start from that 60,000 seconds.
Okay.
I hope so. I have given it for 60,000 seconds, right? Now after the 60,000 second, I'm still not getting. I just change it to, for example, I'll stop
Then we
here.
will continue to
Yes,
apply.
yes. So I'll stop here. So I hope we assume that it is 60,000 is done. MCA acquire setup. I'll give you 1 lakh seconds. Okay. Okay. Now it is set to 1 lakh. So it will continue from where it was left. I need not start it from 0. Okay. Yeah.
Okay.
So we give some seconds. We have basically 30,000 and 60,000 as our standard. 30,000, if you don't get, we increase the time to 60,000. If you don't get, till we don't get, usually we say that it is less than, we calculate the minimum detectable activity and we say that it is less than the minimum detectable activity for that time. Okay, again, minimum detectable activity is dependent upon your time. So when we are saying minimum, reporting minimum detectable activity of your sample, you have to say for the size of the bottle, it is dependent upon the geometry of the bottle, weight of the bottle and time. For example, if I am saying, see, you can see here, minimum detectable activity for 210 lead is 1.7 becquerel per kg for 300 gram and 60,000 seconds. This is how you will report it. Okay. So let us start. So I will give 4 of you can come here, 4 of you can come there. So I hope why we are not giving you a spectrum that is analyzed right now. We will give you a spectrum that has been analyzed previously. Okay, is that fine? So 4 of you can come here, 4 of you can settle there, 4 of you can settle there. So I think that would be 12 and one can join one of the teams. So I will give you uranium spectrum. Okay. Standards. Yes. Wait. Yes. Okay. So 4 of you can sit here. Don't do anything. I'll let you know what to do. Okay. Okay. Take a chair and settle down. Maybe I don't think so. Everyone will have chair, but 1 or 2 can sit in and the rest can stand. Yeah. Or else we can bring chairs. Yeah.
There are several small points when you
Yeah.
zoom in. What are those?
I will tell you. We will explain it one by one. Okay. You can take a chair and sit here. I will explain later. Okay. Ad beda tegiri adalledi. We will use the loaded spectrum, or else I'll have to do the same thing again and again. Okay. Yeah. I will show you thorium spectrum. No, we'll start with uranium, and then we'll do thorium. Then we'll do rest of the cesium and potassium will come in the spectrum itself. Okay. So No, uranium. ಅಲ್ಲಿ ಒಮ್ಮೆ ನೋಡಿ ಅಂತ ಮಾಡ್ತಿಲ್ಲ ಅಂತ. Okay, so you have your spectrum. 4 of you can sit here. Okay, take the chair. 4 of you can sit here. I will let you know what to do. One minute, sir. Sir, I will let you know. I will let you know what to do. Just give me 2 seconds. Yes, okay. Okay, please sit down. Okay, you can take these chairs.
Is it so that all these spectra are same?
Yes, all 3 spectrums are same sample, same geometry, and almost similar time, I guess, 30,000 seconds. So we will. I think someone can use this chair. Okay. Okay. So, sir, can you explain to them what to do?
Yes, if they want to ask.
Okay.
I do not want to automatically interfere.
Okay. So, you can bring the chairs from that lab and sit down. I think that would be better. I think you can bring the chairs from there. Extra chairs you can add and sit down so that. Yeah. No, you'll have to. So give me space to come and explain, and then.
Now you tell what
Yeah,
you have to do.
yeah.
Next
You go and explain to them. ROI clear ಮಾಡಲಿ ಮತ್ತೆ ROI calculate ಮಾಡಲಿಕ್ಕೆ. Okay. So I will explain to them how to set the region of interest. Okay, then they will calculate the counts and then they will calculate the efficiency. Okay. So first, can please listen here. So the first thing that we are going to do here, Vaishak, one. Yeah. So the first thing what we are going to do here right now is calculate the counts under a curve. Okay, under a spectrum. For example, you have what I have given you uranium peaks, all 3 of you. So you will calculate what and all peaks can you get under uranium peak. Can you please tell me? Bismuth 214, yes. Lead 214, yes. And yes, lead 210. Okay, lead 210, bismuth 214, and lead 214. Okay, these 3 peaks you can calculate. So let us see how to do that. Okay, so for that what you have to do is that you have to calculate the region of, we have to set the region of interest and calculate the area under the curve. So I will do it for one peak. For the next peak you will have to do it. Okay, you can start with that. Okay, so I have already set the region of interest, so I will clear all the region of interest. Okay.
So it
Now
is
you can
all-
start.
These are all predefined and you had done it.
Yes. yes. No, fine. Yeah. Yeah. Just give me a second. Okay. Now this is 30,000. See, counting time is over here. So if you get confused, just check here. You have counting time is 30,000 seconds, dead time is 0.17%. So all counting characteristics are good. Okay. Now what you have to do, I'll do it for lead 210, rest peaks you do it. So whatever the peaks are there. So as sir has asked me, so there are so many peaks, right? As you had seen in the list, there are so many radionuclides for bismuth 214, lead 214 and all. But I don't need all those peaks. If I find 2 good peaks, that is enough. So that is why I have taken the peaks with maximum abundance. The rest of the peaks you can see here. See, these are together. These are all together. Which one?
No, sir.
This one. This one.
This is a, sir, this channel, this is the count recorded. This is the count, sir. This is the energy. So here it is recorded as a point. So this means you have to count 100, 200. So more counts are recorded means it is looking separated. It is looking what you will call raised.
Yeah, so this is the counts per this channel. I hope you remember channel yesterday. So this energy, so let me start from here. So this energy 46.6, 45.6 is having 1146 counts. Okay. So the next one is a 1174. So next one is a 1263. So you can see that as the count increases, this will look elevated. So those are the points. Understood? So we want to identify how many such points are there. Counts. Yeah. So how many? So area we have to calculate. This is actually a Gaussian curve. So let us see how we can do it for this one. Okay. Okay. So I will do it down, and this is your zoom. Okay. So you can do here down, up, down, and you can do this one. Okay. Up, down. So you can do. So now when I want to set the peak properly, I want to look at the bottom of the peak perfectly. Okay. So now you can see the bottom of the peak. Now you want to move this one. So suppose I have kept it somewhere over there. You can't find it, right? So move this here and bring both the points to the where you want it to be. Okay. Okay. Now you set up. So is this okay? Is this point setting up okay? Yeah, that is what. So this is where the peak gets down. So when the peak gets down in the both sides, again it will rise, sir. So which is the bottommost point, that is what we have to determine. Yeah. So this is the, see here after this point it is again rising, correct? So that if I go down, then it will go all over. Yeah. So here I can put here, or put here. Anything is fine. So I will here this one is okay, or at least this one is also okay. Yes, sir. I can actually put here. This is fine, correct? This is fine. This is fine. Or I can also increase it because I can correct it from background. If there is additional counts, I can correct it from background.
Same thing you have to use in the background also. Same channels.
As short as possible. No, some people see some people use centroid plus or minus 5 channel, something like that. But this is just like as low as possible. Wherever there is a dip, I can even use this one. This will not make any difference.
This is manual, no? So everyone identify the different this higher and lower peaks.
Yeah. So you just have to identify one lower point because this will get subtracted in your background. If there is additional peaks that you have counted, additional counts are there, it will get separated. You don't have to worry. Now I will do display ROI, add ROI. So this is set. Okay. Now you can check the counts here. So display ROI. So I
But you have to mark it, na?
mark these two this thing.
How to mark
So
it?
select it by mouse. Select this one. So when you get this, yeah, one click, cursor, yeah, cursor. So see,
Right click, huh?
right click, left click,
First
left click.
second right.
No, left click and move.
Okay,
Left click and move.
add to some portion.
Okay, for example, now I'll tell you easier method. I will do easier method. Okay.
Different software will use different.
Okay, no, I will do this. I want this peak. Okay, this one I use left click and bring it over here and press Control L. Control L will bring the left marker. Then Control R will become the right marker. So we usually when it is coming to the right, left and right will come together. When it's going to the left, right and left will come together. So if you
Yes, sir.
yes.
Yes, it varies.
We are using the synthesis spec, sir, for the same gamma.
But basically it is same. Basically it is same.
Working position,
Yeah.
but the system of operation will be different for different
Software will be.
Whenever you get
So
into
can you do this? Can you do this? Can you do this? One by one you have to select, add array, and then go for example, I have added this array.
Yeah, you completely
Okay.
show for one.
I've done this array. So now if I plus minus, it will go to the first one. So this is why we are selecting array. Okay, just do this.
Sir, is there any option to in that particular display, like display, then you have to take all the spectrum for ROI
No.
in our synthesis spec?
I think you are telling about automatic peak fitting.
That is there, but we'll do it manually right now. Okay.
Some software, now recent softwares are coming
Yes,
with
sir.
automatic
Left
peak
side
selection.
and right side. How to mark?
I will come, sir. I think you can manage this. Yes. Yeah.
Control L and control.
One by one you bring. Yes, sir. What doubt?
How to mark left side and
Okay, I'll clear this all. First clear all the. Please don't stand near to this, please. One general instruction: please don't stand next to this area, because suppose you just go like this and something changes. Okay, so keep one chair here. So I think it's better. This is manual, so something goes turns off. It is difficult. Okay, now what I do, sir, you can also watch. So I will clear all the pre-saved region of interest. So I'll clear everything. Everything is cleared. Now it is as fresh as how we get from a spectrum. Now what I will do is that, so the first peak is lead 210, 46.5. So let us go to the first peak, right? So can you see the peak over here? So I can do this one also. So you have options here. You have magnification box over here, and then there is a scroller over here. So it magnifies the region of interest. Okay, now once this is done, so let us say marker is somewhere over here. Okay, how do you bring the marker? So you either take the mouse, select the leftmost marker, click this one and drag it. It's not come. Okay, drag it. But then sometimes it is over this side, somewhere or far away, and you can't drag it all the way from here to here. So what we do, we just select this left end some point and press Control L or Control R. Control L will bring the left marker, Control R will bring the right marker. That's it.
clear.
Yeah.
Okay.
Thank you, sir. Okay. Now what we do? Now we select this spectrum. Okay. I'll just do it smaller and smaller. So now it is much clearer. So is this clear? Is this fine? The lower and both side it is lower. The peak should drop and then it should come level, or it should increase. Can you see this? So for this peak I can select this and this. Okay. So I'm selecting these two peaks. Okay. And display ROI, add ROI. So that ROI is selected. Now you do that. So this is for 46.5. Now you check the area. Okay, 34,000. 154.
We did
Okay.
it already.
Yeah. Now, now you go for the next one.
So next one again clear.
No. Don't clear. Don't clear.
Just dragging the.
Drag and go to just go.
Okay.
For example, next which peak do you want? Look at the alphabetical order. 46.5. Next one is 238. So let us go to 238.
Is the energy calibration correct here?
Yes,
Okay.
it is correct. So basically, we once energy calibration is done, can forget it. You don't have to do it once in a while because this won't change much. So now 236, right? 238. 238 is here. Correct.
But it's 242. It's
Let two. No. 1 minute. Yeah. I think 238 we don't get much. I think it's 242. Yeah. I will leave that radionuclide. Yeah. That is not the energy calibration is correct, but I usually don't take lead 212. Yeah. So I take actinium and thallium. So let's check the next one. Which one? 295. 295 is there here. This is 295, sir. 295.6. It's correct. So let 214 we don't get 212 we don't get much. Now what you do? You want to bring your markers, correct? You brought it. Okay. Now you mark it. You take it this one as low as possible. Okay. You can even put here, no problem. Because then once you do this, once you complete this, you let me know. Once you do all the ROIs, then we can calculate background. So background we use the same ROIs. Okay. So this is control R. And then you can also select insert. Insert will do that.
But I think if there is slight changes to
Left,
part,
no
the area
problem.
will change whether
Yeah, area will change, but we can correct it using background correction.
Is it assuming linear baseline in this case?
No, it's actually logarithmic, but it is actually correcting it actually.
Yes, but I mean that from this point to this point, it should be linear.
Yes.
All right.
So
So basically, this is not a background. This one, this is like a baseline. Background is as
different.
I told in that
no,
lecture.
background we have. So once we select this, we use the same RAI to background. Background there is already one peak. So 1 minute. So for example, one minute.
Centroid is 295. That is the energy.
Okay, so I have background over here. So this is my background.
For that energy region, we have to
Yeah,
take
we
again.
add that spectrum to this one. The region of interest we add to this one, and then calculate the background for the same peak.
So it's automatically done.
Yes.
Yeah, all right.
So actually, automatically also can be done, but here I'm teaching the manually. So first you finish this one, then we can do the background correction. Okay.
All right. Thanks.
Thanks a lot, sir. So is it clear here?
You can zoom it.
No. Did you tell them about control L and control R? Okay. Insert brings that. Okay.
Now I have marked the peak which I want. Now what I do.
So how do you do it in your lab then? Spectrum marking.
So we have an automated analysis process that calculates automatically.
1 minute. Yeah. Yes. Yeah.
Automatically calculates the peak areas. However, what I will explain in some of my presentations how we do it. But we do, in fact, we don't use this ROI method.
Okay.
We use peak fitting.
Oh, okay.
It's a different way.
Yeah.
Of course, the result is more or less same. But for example, in case of 186 peak, then you have to be very careful about the fitting.
I don't use 186 peak at all.
Yeah.
I take it for a comparison between my lead and 214 lead and bismuth values and compare it with it. And if it is not the same, I use the other three peaks and average it.
Yeah. For uranium, 235, I normally use 164.
Okay.
It's the best peak because there are no other interferences.
Oh, 165.
164, 5, something like
Okay.
that.
But we don't get uranium 235 here much.
Yeah, all right.
I have never seen uranium 235 in the peak, or I have not noticed it.
Yeah.
I should gradually rather check it once in a while.
Yeah. But use that peak when you, if you want to analyze uranium. I think it's best.
164.
Yeah.
Yes. Thanks a lot.
Of course, there is another option. If you are not measuring 235, then you can calculate it on the basis of uranium 238.
8. Yeah. But uranium 238 again, HPG is not the best instrument to calculate uranium 238 because we cannot ensure the equilibrium between uranium and radium. So we do uranium in water. There is another equipment I can show you later. We have analyzer in water using a fluorimeter method, and there is a fluorimeter. And for other things, we have to go for HPG. Sorry, alpha spectrometer.
What we are doing in this book, we constantly analyze uranium. I think it's not a problem. Okay, there are problems in some cases, but they are some special cases. So we are analyzing 238 by using this protactinium peak 1001.
Okay.
But the activity of thorium 234 at 63 KAB.
Uranium 238 we don't calculate. For which one? Uranium 238 we don't calculate. Only these. Only this. Yeah, it is. Yeah, yeah.
100 divided by 3000, 100 divided by abundance.
35.
Whether
Yeah.
we get cesium?
You check if you are
No,
getting
we are
cesium.
not getting.
Then there is no cesium. Okay. Uranium RG you might not have cesium.
This is bismuth.
That is bismuth 604, 619. Huh? Yes, but uranium peak is not there. Uranium as a peak, uranium 238 as a peak, I think there is one at 64 or something. 64, 63.
50 some.
Yeah, but it is merged with other peaks. So we cannot calculate uranium directly. So you can only. Huh? That is radium 226. So see, I'll tell you the difference. So you have uranium 238. It gives proactinium, all those things, all this. Then it comes to radium 226. Correct. From radium 26, it will go to radon 222. Okay. From here, it will come to bismuth 214 and lead 214. So we ensure these two are in equilibrium by keeping it to 27 days. Okay. So now using these, we calculate radium 226. So, but we don't know whether these are in equilibrium, radium and uranium. So we cannot say that it is uranium 238. We give the results for radium 226. I hope you understood. If these are equal, if uranium and radium 226 concentration are in equilibrium, then I can say it is uranium 238. But until and unless, we cannot say that because there is no gamma emitting radionuclides that is as good in between.
What our practice, sir, that is sodium iodide detector. So that is thorium is that is calculated as a line level.
Okay, that is actinium 220. Yeah.
Then uranium is it's equal with bismuth.
1007.
Once it is done, we are storing the RO. Store. So we have to name it.
Bismuth 214.
Bismuth 214 at 1120, right?
1120.
That is actually radium, as I told you. You cannot say that is uranium. You cannot say that is uranium unless you know these two are equal. Uranium and radium are equal. You cannot say that it is uranium. Bismuth 214 gives you radium 226 active. Okay. Yeah, you cannot say it is uranium. You can say it is uranium 100%. But uranium, you cannot say it is uranium. 100. Vaishak, let them do. Let them do. ಅವ್ರು ಮಾಡಲಿ ಅಂತ ಆಯ್ತಾ ಬ್ಯಾಕ್ಗ್ರೌಂಡ್ ಸೊ ಕೌಂಟಿಂಗ್ ಟೈಮ್ ಡಿಡ್ ದೇ ಚೆಕ್ ಕೌಂಟಿಂಗ್ ಟೈಮ್ ಓಕೆ 1 minute I'll come just look at the peak I'll come
ವ್ಯಾಕ್ಯೂಮ್ ಕೊಟ್ಟೆ
ಹಾ ಹೌದು
ಇಡದೆ ಕೊಟ್ಟೆ ಮಾರೆ
ಈಗೆಂತಾಯ್ತು
ಅಲ್ಲಿ ಎಲ್ಲ ಇದ್ದಾರೆ ಸ್ಯಾಂಪಲ್ ಇಡಬೇಡ ಅಂತ ಕೇಳ್ತಿದ್ದಾರೆ
ಯಾರು
ಅಲ್ಲಿ ನಾನು ಸ್ಯಾಂಪಲ್ ಮತ್ತೆ
ನಾನು ಬರ್ತೇನೆ ಸ್ಯಾಂಪಲ್ ಬರ್ತೇನೆ
Take the marker here. So it gives ROI information, you will get it automatically. Just all this left marker, right marker, centroid. What is centroid? Peak. Yeah, peak. Area is area. Got it? These are, see, what you get here is specific for this software. And if you use some other software, for example, RTEC, or you use DSC spectrum, DSC. Then the report window will differ. That's why you should be knowing what you are doing. If, of course, there is a software which doesn't give anything like this. Then you should be able to manage that. So that you should be knowing from where to take the counts, how to take the counts. In our time, when I was a student, we had what is called single channel analyzer, and then we had 1K multi-channel analyzer. So what used to write, we used to have a book which is 100 times this, and I used to write like this: channel number 621, 622, counting up to 640, and I used to write the counts down. Then I average. Now software has become very user friendly. It gives. That's why students of today are much blessed with technology rather than what technology can do. Technology grows means they cannot do it manually. Yeah. So this is what basically this is what area is, what is integral is. And then we used to do the quantum contributions for ours. Right, come. Yeah, I was telling them how to take the count. I was instructing them how to read the spectrum. Yeah. You already know how to do so. All of you have seen the live spectrum acquiring? Yes, they have seen, is it? Cesium and cobalt. Yes. So note down these things. Tomorrow when Roy talks, he will be doing what are the different efficiency corrections we have. How you evaluate spectrum like this. That is the advanced. That is what we mean by advanced. Now you are in the basic level. So you have about 12 hours from climb from the basic level to advanced level. Do it now. And don't worry, if you want to be here overnight also, no, it's possible. And at the end of the week, you will find that this course is 1 week course. The 1 week is not enough. You will feel that it's 1 year course.
Broad subject.
Yeah.
Very broad subject.
Yes. Yes. Those who are working in the field, they will appreciate this. Those who are new, they will feel it is strange. Yeah. Yeah. What am I?
The background.
Background. Is already over. So what you want to data set background is already over. Yeah. For the same corresponding same note down the background. Please limit your skills only to note on the spectrum, not to change
Now you mark yourself.
Control L.
So that time I was, I stored right here, 46.67 plus. Ready? Okay. So that will work. So next we can see which one will be right. Okay.
Just
No, first keep control L.
control. Again, automatically add on.
Then you do this tab.
Control L.
You click there and do this space tab.
Okay. Now
Or else you can do like this. You can press here.
Control
So
R.
you can move the music. There is no like press here.
right. Early right R is like.
Then you will get a point.
Now you go to add R.
Here.
Add first.
Since I loaded ROS, it will come. Or else you can press I already loaded ROS will come.
Area is 204950. 4504950. Three four nine three two. 3493. Again 3539. First one is 9493.
So marking is manual. So you have to delete ROS. Again you can adjust the person.
Clear. Just
This one. Become separate. Or else you can put the person because to put the person using control level.
Okay, there is no.
particular one of the
Zero.
Sometimes it comes and it goes to the control level. Control level 1764. It is marked. So you have to press it. Yeah, it's marked. Count down. 4 6 not.
If you want, but then you it was control 606 control 619.
Just a line. Now you can easily. Yes, but this is not great anymore. You have to just line to line. Check the center. See, so you can adjust the area. Continue marking. We were thinking how to calculate these very small areas. Practically, this is practically the area is quite close to zero because if you can see here, the true peak area is 100,000 something. So there is no significance. The capital here is 10 or 20. We can put it 0. It's already stored.
Did you add arrows? How the arrow is save ಮಾಡಿದ್ರಾ? Did you delete it? Close it. It should be here. It is here, right? This is the other one. Correct. Correct. So now this is RY store and let us put GIAN. Okay, GIAN for there. So I think we need GIAN 2024 because there was GIAN 2018.
That time I was giving the
Now, we'll put the RI name. What is your some name? No, you are what is your formula? Okay.
No, we have to.
For which? So this is for uranium, right? So now I now I go to back display what is the GIAN? Now you get the same mark. Got it? So do it for thorium. After you've done uranium heating, I'll give you thorium. So RA adding is done. So for all uranium peaks you have done. Now, sit. So we will go to display ROI store. So whatever region of interest you have added. So how many you have added? You have added only 46. 351 is there. 608 is there. 176. This you can actually have here. As this is the lowest, that would be much better. We can add it over here or over here also. But again, it will get corrected in background. If it is so, as long as you don't put your ROI in between, here whatever you put background correction, it will clear it out.
That is channel.
You put here. Now,
Probably make, but you need to add one more point as you said the last one.
you just had some ROI over here, no? See, here there are two ROIs. There is one here that you have added, one that I have added. So I can just from here, I can just take this one and put a cursor over here, and then put the same thing insert. You will get
Background.
yeah. So now there is 3 ROI for the same thing, but it will confuse you, right? So we will remove the other 2. So next, this ROI index is there, here minus. So it will went there. So this one we don't want. Okay. And here this one we want. This one, yeah. This one. There is one. So this one also I did it. Yeah, the simplest. Yeah. Now again I did it. There was 3 ROI in that. One you did, one I did, one sir did. So one here. Yeah, display ROI. Delete ROI.
Undo.
No. No. There is no undo. Okay, now this is done. Okay, we will store ROI. So I will open a new folder. Yes. One of your name. Amina. Uranium. Okay. Save. Okay. Now we will open one background. Once, twice in a month is enough. Yeah, that also you can do. That also. Okay. So you have taken the counting time. Counting time is important. It is 30,000 seconds. Okay. Right, see, uranium counting time 30,000 seconds. So counting time is important. Without counting time, you cannot get see this one.
There is no background. Okay. For that,
Now we will do one thing. We will have to open the background, right? There is one background here. This is 2023. This sample is 2021. So we will see during that time what background we had. 2019 I have background. It will be somewhere. I'll have to check. 2020.
search for thorium.
Anything you can use, but it is better to use the same background during that time. So that I use background every month. I name background as BG. 2023. Let's see so many 23, 22, 21. BG.
This background is for 67. Write down the time.
BG for 90,000. So this is your background. Here you can put R. Oh, you asked for actually. You asked for. Yeah. You finished. That is better.
Now you can identify thorium.
So RGB is this. Background is there. I will give you thorium.
So we can
Here is thorium.
So this we counted 30.
This is
Like counting time.
Time.
Background.
thorium 142 grams. This one. Here is this file. This is cap standard.
That is the count. This we counted for 60,000. That is later. First we have to
This is your thorium. So you do for uranium and thorium. For cesium you might not get. Cesium I'll tell you how to get.
differences.
Standard. K40 and cesium I'll tell you how to get. Okay. We can actually get RGK is there, but we can do from the graph also. Okay, that we will do. We'll do. Yeah, extrapolation. So you do thorium. I will clear all the ROIs. Okay. So background, I think you will have to take different background. But you take background later. Okay, now you take the thorium first, then you will see.
That 212.
258. 38.
Look at the weight of the sample also. So weight is given over here. Uranium standard is 138.8352 gram. Right sample. 138.8352 gram.
Reduce it.
Thorium weight is 142.1157. 1157. I will give you the activity for uranium and thorium in becquerel per kg. Then you will have to do whatever is necessary. I tell you what it is necessary, but you think what you have to do. Okay? So thorium. Yes. Thorium.
I think it was if I select left side here, right side on this, so does it show that this or
But so what I do is that
because you have to know this if you want to calculate the area of the leaves. Software calculates average value of baseline here, which then okay, it may be this one or this one depending on the level. But I have to find out which one is correct. Okay, if the peak is very big, then there is no.
yeah. So that is why what I do is I only take the peaks which are raw good, like very good peaks, very big peaks. Smaller peaks, let us say we're getting 100 much, I just say that as
ಅವರಿಗೆ ಟಿ ಬೇಡ ಅಂತ ಯಾವ ನಿಮಿಷ ಟಿ ಬೇಡ
I think how
later
Whenever they will.
yes okay how guys how rather you give a break for tea now you break for see all of you we break for tea for 5 minutes accepted all of you all the participants we are breaking now for tea 5 or 10 minutes and we are coming back immediately okay how is it going, Roy? Yes, yes. They want to. Yes.
I have to.
Yes, yes.
I think you can answer that question.
Yeah.
Okay.
Yeah. Stay quickly and come back. So there are a lot of work to do. Yeah, I know you don't want to leave, but quickly. Okay. So we will do have quick tea and then come back and then see why I don't take immediate gadgets for this. Understood? Yeah. But you can do that, but still where you can take the lower point is nice.
Yeah.
And then we calculate the sum.
Correct.
Or you can do it.
However, if I select left being here
Yeah.
and right side here,
Yeah.
so does Jenny do it like this way or does it this way?
Yes. I let me go through this their manual and find out this because I am also not very certain how it does.
If this peak is very big,
Yes.
then there's no significance.
Yeah. No significance.
But if the peak is very small,
Yes. Yes.
then you have to know
Yes.
which method is.
Yes. I will find out and I'll let you. I have a book, Jenny user manual, and I will find out. And I'll get back.
They have to know. I mean, your
Yes, they have to know. This, yeah, how it is done. Yeah, very important. Yes, you are right.
all right.
Yes.
So we know that I
We'll talk about it.
ಈ ಒಂದು ಜೆನಿದು ಸಾಫ್ಟ್ವೇರ್ ಬುಕ್ ಉಂಟು ಕಸ್ಟಮೈಸೇಷನ್ ಮತ್ತೆ ಯೂಸರ್ ಫ್ರೆಂಡ್ ಅದರಲ್ಲಿ ಕೊಟ್ಟಿದ್ದಾರೆ
ಸರಿ.
ನೋಡ್ ದೇ ಹ್ಯಾವ್ ಗಿವನ್ ಆಲ್ ದಿಸ್ ಇದು ಈಗ ಬೇಸ್ ಲೈನ್ ಇಲ್ಲ ಅಲ್ಲಿ ಅಲ್ಲಿ ಆಗ್ತಾ ಉಂಟಲ್ಲ ಅಲ್ಲಿ ಇದ್ದಾರ ಆಲ್ಫಾ ಕಟ್ಕೊಂಡು ಸಣ್ಣ ಆಲ್ಫಾ ಕಟ್ಕೊಂಡು CPS by DPS. That's all. CPS by DPS. And other terms are always because you are in for 100% division or 40%. So if your simple efficiency of a detector is CPS by DPS or CPM by DPS. You ask, last time now this area under this divided by